Can we get the mic? Okay, this should work now. There is more space in the front if you want to sit down. Unless you want to change sessions, then stay where you are. Yes, welcome to this session, number 13, on detectability of non-linearities, abrupt shifts and tipping points in marine ecosystems. I had to check up the title again myself. My name is Friederike Fröb. I work at the University of Bergen. I'm a postdoc. And I have the pleasure to open this session now together with my co-conveners, Camilla Squatti and Thorsten Blenkner. Yeah, and you should talk.
Yeah, good morning, everyone. Welcome to this interesting session here. We're going to have quite some broad topics from like region on tipping points and maybe non-linearity, some questioning of tipping points, abrupt shifts, and then also on some particular fish species. So it's going to be quite an interesting session until today, 5 o'clock. So please stay tuned until the end. We're going to have some fun here. So, but before we start, I would like to start with the keynote speaker, which is Maren Hunsicker, which is fantastic that she came here. She's from the Northwest Fisheries Science Center, NOAA, and she has been working there for quite some time, but also being a postdoc at the NCS in California, where I met her also in some workshops. And she has been working and published quite some papers on non-linearity, tipping points, and so on, but also very much interested in the change in structure and function of marine ecosystems. Mary, the floor is yours.
Great. Well, before I begin, I would like to thank the co-conveners for inviting me to give a presentation today. I would also like to just acknowledge my co-authors on this talk. And so my plan for today is to talk about some of the work that my colleagues and I have been doing to advance the science around tipping points. And I'll be talking a little bit about our work we've been doing on ecological thresholds, as well as our work on developing indicators of ecosystem state in Northeast Pacific systems, and also be talking a little bit about the challenges of this work and some future directions. So the term tipping point is implied in many systems, from ecology to climate systems to economics and social science. And there's other related concepts to tipping points, such as thresholds and regime shifts and ecosystem shifts, which I'll be using today. And I thought I could start out by just providing one definition of a tipping point, which is when incremental changes in human use or environmental conditions result in large and sometimes abrupt changes in ecosystem structure, function, and benefits to people. And there's been increasing attention on tipping points in our scientific literature. There have been a number of perspectives and review articles warning of tipping points and calling for the need for more research on tipping points, especially in light of global climate change. This figure on the right shows a recent paper from Limnology and Oceanography, which shows the number of papers from marine, freshwater, and terrestrial systems that include the term tipping points or related concepts in those papers. And what we see is that over the past couple decades, there's been a rise in these types of papers in all three systems. And I'm sure if we had a climate systems on this figure as well, we would see a very similar trend. Because of the large and abrupt impacts that tipping points can have on human communities, especially those that depend on marine systems for their food and livelihood and cultural heritage, we're seeing more language on tipping points in our national and international climate assessments. For example, in the most recent version of the US National Climate Assessment, we're seeing more language on tipping points and the need for understanding and monitoring climate-driven transformations than we've seen in any of the past reports. And we're also seeing calls for more science around tipping points from our government agencies and our funding agencies. So within marine ecosystems, there have been many examples of tipping points across different geographies and habitats, including coral reefs and kelp forests and pelagic systems, for example. And the examples are continuing to grow. And many of the authors of these papers have documented shifts that have lasted for decades, indicating that when recovery is possible, it can take a while. So given what we know about tipping points, my co-authors and I and other collaborators, as I mentioned, are interested in advancing the science around tipping points, particularly with respect to anticipating ecosystem shifts so that we may be able to better mitigate and adapt to the potential impacts. And so today, as I mentioned, I'm going to briefly talk about some of our work on ecological thresholds. Then I'll talk about some of our work on ecosystem state indicators and some work on non-stationary relationships related to ecosystem state indicators and some future directions. So there's different approaches and methods for defining ecological thresholds. My co-authors and I have been focused primarily on looking for thresholds in pressure-response relationships. For example, this conceptual figure here shows a threshold in the response of ecosystem variables to fishing and environmental pressures. And this threshold indicates that there's a rapid change in an ecosystem variable with a very small change in the pressure variable. And so if this threshold represents a change from good to poor conditions, we may be able to use it to identify a target for triggering management strategies or monitoring strategies that can help prevent the variable from shifting to a poor condition or planning to adapt to that shift if it does happen. One of the methods that we've been using to detect thresholds in marine systems are generalized additive models, or GAMs. So this is a paper that Scott Large and authors published several years ago in which they fit GAMs to several pressure-response relationships into the Northeast Pacific. And then they quantified, Northwest Atlantic. And they they quantified inflection points in these nonlinear trends to be able to estimate thresholds for particular variables. And so they found evidence of several thresholds. They found evidence of thresholds in several pressure response relationships in this system. And then following the Large et al. Paper, several other papers started investigating nonlinearities and threshold responses in US and Canadian systems, and I'm sure elsewhere as well. And these authors found thresholds in the responses of other biological variables, such as copepods, anchovies, sea lion, pup production, and ecosystem trends to different human and environmental pressures. And while these authors did detect thresholds in these systems, they also found that they weren't very common. And there's also been some debate in our literature about whether we can actually detect thresholds in empirical data. However, we do think it is important to continue to pursue these efforts because there can be high social and economic costs associated with missing thresholds when they are there. So my collaborators and I are now interested in taking sort of a step back and expanding our work into trying to figure out ways where we can try to help increase the uptake of threshold information and management. And we think there's a couple different ways that we may be able to help with this. The first is that we think simulation studies are needed to demonstrate how incorporating thresholds in management applications could improve knowledge of risk and uncertainty and thereby improve decision making. We also think that simulation studies that analyze the sensitivity of threshold models to non-stationary dynamics, observation error, short length of time series, and other factors are needed. Being able to recognize and communicate where thresholds are robust or not would help instill confidence when using them to make management decisions. Further identifying underlying mechanisms through which thresholds may or may not arise could help advance the uptake in management, as well as the co-development of management on-ramps for threshold information with stakeholders and management partners. So now we'll talk about some of our work on developing and updating ecosystem state indicators in the Northeast Pacific. So the impetus for this work is that there have been a series of marine heat waves in the Northeast Pacific over the past several years. And I'm sure most people in this room are aware of the very large marine heat wave that occurred in the Northeast Pacific between 2014 and 2016, and also had some important ecological effects as well as impacts on the fisheries in this region. And so at that time, there was concern about whether this heat wave would push the system into a different regime or a different state. Also, given that we're expecting to see more heat waves within this system, there's interest in finding ways that we might be able to detect the changes, the ecological changes of these heat waves and other perturbations to the system as soon as possible, and to be able to track those changes. In addition, many of the indicators that we use in our ecosystem status reports in the Northeast Pacific really are, many of them are focused on single taxa. And so our idea is that by summarizing information across a broader set of taxa and life history stages, we may be able to provide some important broader level ecosystem information about these systems. And so to do this, as I mentioned, we're developing these community state indices for Northeast Pacific ecosystems, where the goal is to be able to evaluate changes in mean community state in response to climate perturbations. We'd also like to be able to distinguish normal variability from changes signaling a major shift that could then hopefully be able to help provide some early detection of abrupt ecosystem level changes. And so to do this, we've been using a method called dynamic factor analysis, or DFAs. And if you're not familiar with this method, it's a dimension reduction tool similar to principal component analysis that was designed particularly for time series data, so it can account for autocorrelation in the data. And we're using this method because we have a bunch of noisy time series, either climate or biological time series, that we want to use to be able to identify whether we want to be able to identify whether there's latent or shared trends within those time series that might be useful as an index. And the idea here is that large changes in those trend values may indicate large changes in the underlying community of the shared trends. I'm not going to go into detail about this method. I encourage you to if you're interested in it, you could check out these papers by Eric Ward. He and Sean Anderson led the development of this method, but I just wanted to highlight a couple things. The first is that this method handles missing values in time series, which is pretty common in ecological systems. This approach also includes an algorithm for identifying states or different states or regimes in the estimated shared trends using a hidden Markov model. And we've also extended this approach to be able to create, or at least we're testing our ability, to create one-year ahead forecasts of these ecosystem trends. So for today, I'm only going to have time to really dig into one case study, and so I'm going to focus on the central, South and Central California current system. And so the particular objectives for this case study were to summarize environmental and biological variability in this system and potentially try to see if there's evidence for regime shifts in the system. We were particularly interested in evaluating that idea, whether there's a regime shift following that large marine heat wave in 2014 and 2016. And then we're interested in identifying whether there's relationships between community variability and climate variables. And we also, again, want to test our ability to create one-year ahead forecast of the community state. And so quickly, I'll just mention the different data that went into the system included climate data from a regional ROMS model that was developed by Mike Jaycox and colleagues at the University of California, Santa Barbara. We also included about 32 or so time series of biological data, including ichthyoplankton, juvenile fishes, seabird reproductive success, and sea lion pup growth and weight, for example. And so our approach for this was to apply separate models, DFA models, to the climate and biological time series, and then use model selection to identify the number of trends, the error structure, and other components of the model formulation. And so here is the first results that I'm showing from the DFA model that were fit to the climate data. The figures don't look as good as they do on the computer, but the figure on the left shows the climate trend. So a one-trend model was the best model. And what we see from the climate trend is that it does capture some of the perturbations and captures the El Nino events within the system, as well as that large marine heat wave, the 2014-2016 marine heat wave. And then the figure on the right here shows the loadings, which link the time series to the shared trend. And so, for example, those loadings that load positively on the trend, like sea surface temperature, sea surface height, and stratification, are increased where we see these peaks in the trend and decreased where you see the valleys. Whereas the other climate time series, such as mixed layer depth, upwelling, and nitrate flux, that are looking negatively on the trend, are doing the opposite. So they're lower where we see these peaks in the trends and higher where we see the valleys. And this matches up pretty well with what we know about the ocean conditions during the events. We tend to see warmer temperatures, reduced upwelling, and reduced nitrate flux, for example, during those events. Now, as I mentioned, we have this algorithm where we can detect different regimes in the shared trends. And so this figure on the right is showing the results of that algorithm, which essentially assigns a probability of the shared trends being in a particular state. And so for the climate state here, what we're seeing is that, between 1980 and 2022, the climate is just kind of bouncing back and forth between these two states, essentially bouncing back and forth between warmer and cooler conditions. So for the results of the biology, again, we found that a one-trend model was the best model. And we see that there are deviations in the community trend around, again, these El Nino events and the marine heat wave. And then when we look at the loadings on the right here, we see that there's a lot of coherence in the biology in terms of the response to some of these to the climate perturbations. So for example, around the time of the marine heat wave, there was an increase in the rockfish species, some anchovies and flatfishes, mesopelagic cephalopods, for example. But during that marine heat wave, there's also a decrease in the sea lion pups' growth and weight, as well as a decrease in adult anchovy and adult sardine. And this mostly matches with what we saw, the observations that we were seeing within that systems around those times as well. And another take-home point from this, we were really interested in, again, evaluating that question, did we see a shift to a different state following that marine heat wave? But based on this trend and based on this regime detection method, it doesn't look like the system has shifted to a new state. It's mostly capturing the responses of the community to those El Nino events and the marine heat wave. So similar to the ecological thresholds work, we're interested in figuring out ways that this information might be useful within a management context. And so our idea sort of thinking through this is that it would be great if we could use, we could use the survey data and the indicators that we use for ecosystem status reports and combine that with 1 year ahead forecasts made of the ocean conditions from the ROMS model and use those to develop forecasts of ecosystem state. And then if we are able to do that, can we then say anything about the future recruitment and survival of particular species, managed species that the managers care about, like salmon and groundfish, for example, or also conservation species that are important to us? And then this information could then potentially feed into assessments that could help inform monitoring strategies as well as risk tables. And so to get a little bit closer to this, we are trying to test our forecast skill of ecosystem state. And to do this, we're essentially testing whether the models that just have the biology time series, we fit models just to the biology time series and then a model to the time series that include a single climate covariate and determine whether the models with the climate covariate outperforms the model without. And so, for example, this figure here shows the result, the trend of a model that includes sea surface temperature with an out-of-sample forecast for 2022. And I will note that when we did this, several of the models that included the single climate covariates outperformed those that didn't. And so, for this example, then we went ahead and we developed 10 additional years of the forecasts and the community state, just to see how well it would perform over time. And from this figure, it looks like the forecasts match up pretty well for the true community state. In some years, it's okay. For other years, and in other years, such as 2019, we don't do a good job at all. So this is still something that we're still working on and trying to improve how we're developing these forecasts. One thing that we are working on as well is trying to incorporate multiple covariates into the models to see how they improve model outcomes and the forecasts. So now I'd just like to touch briefly on some of the work that we've been doing related to non-stationary relationships related to our ecosystem state indicator. There have been a growing number of analyses that have shown evidence of non-stationary relationships among physical variables and climate variables and ecological indices, for example. And many of these studies have come from the Northeast Pacific, and particularly the Alaska region. And so we've been doing some work of looking for non-stationary relationships related to our ecosystem state indicator and this dynamic factor analysis. And so I'm going to use the Gulf of Alaska example that we've been working on. We're pursuing this type of work in the California current as well, but I'll just go with the Gulf of Alaska example. And so this here is showing the shared biology trend in the western Gulf of Alaska. This is updated from Mike Litzau's paper in Progress in Oceanography. This trend is essentially capturing a change in the system that had a lot of capelin and shrimp in the early 1970s, but then later in the time series, there were fewer shrimp and capelin and more salmon, jellyfish, pollock, et cetera, more groundfish in the system. And this is a pretty well-known shift in this system. The species are really responding to a climate regime shift around this time. And so we were interested in seeing with this paper, do we see any sort of relationship with these biology trends with climate variables? And particularly, are these relationships stationary over time or not? And so what Mike did is he fit these relationships between winter sea surface temperature and the biology trend over 3 different time periods. So they're shown in green, blue, and orange. So the green was in the 1970s to 1986, the blue sort of that middle period, and the yellow, the more recent period. And what we found was that the relationship between the winter sea surface temperature and the community trend actually changed over time. And so this provides some evidence that we need to be careful about when we're trying to create reliable forecasts, because we may not be able to do so if some of these relationships that we're using to sort of create these forecasts are breaking down over time. So it points to the need to investigate more, put more time into investigating some of these relationships for sure. In addition, we wanted to test whether the relationships among the time series that were using these DFA models, if those relationships were stationary or non-stationary over time. And so we fit these 25-year rolling window correlations between the biological time series and the trend. And what we found is that these relationships also are sort of non-stationary over time. So for example, for cod and jellyfish and the eulachon, the correlations are fairly strong at the beginning of the time series, and they sort of dip down, even changing sign, and then come back up a little to where they're not strongly correlated. And for other species, such as shrimp and capelin, there's sort of strong correlation at the beginning, and there's a monotonic decrease over time. And this has important implications for our work, because one of the assumptions when we're interpreting sort of the changes in these community variables one of the assumptions that the changes that we're seeing are stationary over time, and this is sort of indicating that assumption is not true. Another way to look at this that might be more intuitive or not for others is that we fit separate DFA models to the earlier part of the time series that sort of crossed that biological regime shift, and then to the latter part of the time series that captured that time of the marine heat wave. And then if we look at the loadings for those 2 time series, what we see is that for some of these species, such as pink salmon, eulachon, pollock, jellyfish, for example, their loadings actually changed sign between the earlier and later time periods. For other species, such as shrimp and capelin, the loadings weakened between the 2 time periods, and then there were a whole suite of other species for which that the loadings remained the same. And again, this is important because it's sort of violating that assumption that when we're interpreting what the community variability underlying these trends, we're assuming that it's stationary over time, but it's actually not. So we have to be careful in terms of how we are interpreting what these DFA trends are telling us, what's happening underneath. Okay, so to sum up, there's a need to advance tipping point science to mitigate and adapt to their potential impacts, especially in light of the changes in ocean conditions that we're witnessing and sort of the expected changes with climate change. Also, detecting ecological thresholds may be one way to help anticipate ecosystem change. And even if they're somewhat rare, it's still worthwhile to pursue efforts to detect thresholds in these systems due to the high potential costs of missing them. Also, developing tools that can track and forecast ecosystem shifts could help inform better and more rapid management decisions. And this is something that we're really trying to get at with our ecosystem state indicator. And lastly, non-stationary relationships can challenge our ability to anticipate thresholds and forecast ecosystem change. And some of this knowledge from many other studies, as well as ours, highlights the need for more investigations into these types of relationships and for improving our statistical models like DFA to account for these non-stationarities in the system as well, so we can produce reliable forecasts and interpret them more accurately. So with that, I would like to just acknowledge some additional collaborators who have contributed to this work and have provided feedback on this work. And with that, I'll thank you for coming and for your attention.
Thanks a lot, Mary. If you have any questions, I would like to ask you to come here to this mic and ask the question, because it's streamed also with online. So do you have any questions to Mary?
I'd also mention I'll be here all week, and I'm happy to answer any questions outside of this time as well. Yeah.
What I was missing in your talk was mechanism behind resilience. And I think it's, if you're going to identify the tipping points when you have gradual environmental changes, you need to know something about resilience. Could you comment on that?
Yes, I mean, I definitely agree about particularly understanding the underlying mechanisms, and that may also help us with the issue of non-stationary dynamics. If we're looking a lot at these statistical relationships without knowing the underlying mechanisms, then it's going to be really hard for us to deal with these non-stationary relationships. But understanding that should help us get a little bit closer to that. So I agree with that, sure. Yeah. It's hard to do, but it's definitely important to do.
Thank you. Is there another question? Yeah, please.
Yeah, thanks a lot for a very nice talk. So I was just wondering, when you talk about incorporating this into management, are there any attempts to quantify what this might mean in economic terms? So if you do have the information, how or when this might pay off in terms of better or more stable economic profits? Do you have any collaborations with, I don't know, bioeconomic modeling on that side?
That's a great question, and I think that would be very effective, but we have not gone to that point with our work, but it would certainly be something that I would be excited to explore, and I think it's important to explore. I will say, in terms of looking at costs, there's a recent paper by Adrian Steer and authors where they looked at the value of those precautionary buffers around the thresholds where I showed those pressure response relationships, and the value of that in terms of monitoring costs. So, for example, if you're kind of far from that buffering region, maybe you won't need to spend as much money monitoring your system or your species, but as you're getting sort of closer to that buffer, then you can have higher precision monitoring. So they provided a nice analysis of how, at least in terms of monitoring costs, this could be useful in that way.
Thank you.
Yeah.
Thank you. We have time for one more question. Okay, then I have a short question. I was wondering about the cacophony. Do you think that there's a difference in the response of species which are used to quite a lot of variability compared to a system in Alaska where you maybe have not that strong oscillations?
That's a good question. Although, it's a good question too, because I'm trying to think about this. I'll think about it more. But when in our first paper on this, we had actually extended the time series back to the 1950s, and between 1950s and 1970s, most of that data is dominated by the ichthyoplankton time series. And when you look at that, you do actually see a regime shift in the system that was mostly driven by those changes in that community, that ichthyoplankton system. So they did experience a shift during that time that seemed to, at least with our analysis, sort of drive that trend. But yes, I'm not sure. It's a good question and something for me to think about more. Yeah.
Okay, thank you very much, Mary. Thanks again for your talk. Now we're moving to our next speaker, who is Tsuyoshi Wakamatsu, and he's talking about detecting abrupt shift of Arctic Ocean pelagic ecosystems in the 21st century with dynamic ecoregions. Welcome, Tsuyoshi. Pardon me?
10 minutes?
You have in total 12 minutes to
12
talk, and then
minutes?
there will be
You give me a...
for questions.
Okay.
There will be something in the line saying that
Yeah.
how much time you have.
Okay, all right, thank you. There's a timer. Okay. Hi, good morning. Welcome to Bergen. This topic is developed under the Comfort project, which I started 4 years ago. And then I'm quite new to actually the ecosystem model. I'm a physical ocean, especially modeler. And then we approach to this tipping points and ecosystem in a very different approach. And then the main purpose of this study is, first, Arctic Ocean is facing to the severe environment change in the next, well, not 100 years anymore, next 80 years, towards the end of the century. And then we have many CMIP 6 or CMIP 5, the model prediction, but how we can use the information for this detecting the abrupt change in the environment in terms of ecosystem. And the second one, many studies already work on this CMIP 5, 6 model output and found that in Arctic Ocean, especially in Arctic Ocean, founding the information to analyze the ecosystem, nutrients level, and the primary production are quite uncertain. It's a big, so how to mitigate this situation to come up with some more reliable information. So that's two objectives. So analyzing ecosystem in a large ecoregion is a very accepted concept nowadays, starting from the very big study done by Longhurst, dividing the world ocean to many ecoregions, and then the summarize information, observation, and model output based on those the distinct ecoregions. And that is quite a successful concept because compared to the physical oceanography, biological and fishery, data is quite sparse. So the condensing the information to in a lower dimensional space is very important. And for example, this is a CAF, the conservation, the ecoregion map. And then since 2011, they published a report based on this divided ecoregion. But even the paper mentioned that exact boundaries may change over time to reflect changing biophysical conditions. So going back to the Longhurst definition, the ecoregion is defined by, it is characterized by coherent physics forcing and environmental conditions. So when we see that this, the founding environment changing, and then this ecoregion, you cannot see as a static entity. You have to interpret it as a dynamic. And then, so that's the point. But we have to see that how this ecoregion may change in the future, we have to have a data from the model output. And CMIP 566 is the main resource for everyone for us so far. And then on the right, 2013, based on the CMIP 5 model output, they found that in the Arctic Ocean, nitrate concentration and the primary production are quite diverse. And then one of the reasons is that the Arctic Ocean, the saturation of the nitrate to the steady state takes a very long time. And every time, depending on how you start up the model or how you set up your, the ecological model, it's really change the condition. And then that will really change at what time you will have low nitrate in the future or too much nitrate in the future, interacting with the Arctic sea ice loss. And then the situation didn't change even when we have a CMIP 6, the model output came out. Well, this is the most recent paper analyzing the world ocean ecosystem and the biochemistry. And the Arctic Ocean, this is a relatively the percentage of the uncertainty, by the way. Arctic Ocean is the largest uncertainty in terms of relative the uncertainty compared to the current condition. So we have many uncertainties in the input model to define the ecoregion. So, so as a physical oceanographer, so we decide to use abiotic parameters to define the ecoregions. And there are many justifications for that. I don't have time to do that, but basically, the environment defined by the physical environment, temperature, stratification, and nutrient uptake even is defined by mixed layer depth, which is related to the physical condition. So that we use information. So this is the approach we use. We use the SOM classification to classify the CMIP6 output data. And then specifically in this study, we choose the Norway SM2, the MM model. And then this model is known to have one of the most precise the surface Arctic Ocean condition compared to the reanalysis. And we use a mixed layer depth, surface salinity, surface temperature, and shortwave radiation at the ocean surface, and then topography. And then also, we also define the seasonal change of each parameter, except for topography. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. And then bin the decadal mean average data out of the CMIP6 model and put in the SOMO. And then now we define the 10 other regions, other ecoregions, and then and observe what we will see. So here's the result. So the top corner, and that's our ecoregion defined by the CMIP6 output. And then in the 2020s, so around our time. And then many ecoregions used in the past ecosystem studies, well, mainly they defined subjectively, half objectively, using the topography and geographical change, and also the water mass change. And then it's not so bad to my eyes. So we have a confidence that then maybe we could extract the ecoregions in Arctic Ocean very objective way by using the SOM classification. So here's then the time series of the time series. The fraction of the ecoregion occupy the Arctic domain. Arctic domain is defined by this colored on the map, and so starting from the 1950s, and we have this fraction 0 to 9, so 10 ecoregions. And for example, the Central Arctic Ocean has the largest the occupation, and then there's another one in the Arctic, Atlantic Ocean. Is that pointer, this one? Yeah. So this one corresponding to this, for example, this is the Atlantic water ecoregion. And then you can follow how the fraction changes over time up to the end of the century. And then you see that by the end of the century, you end up with very different the relationship in terms of fraction of each ecoregions. And then you can follow this ecoregion in terms of the not only fraction, but you can follow Lagrange way where the ecoregion moves to. So now we have a tool to map how dynamically this ecoregion could change. And so we could identify, it's not totally new identification because we know that what's happening in the Arctic Ocean, but from this, we see that the abrupt shift, not abrupt, but the complete shift of the ecoregions. We identified at least 3 on the Eurasian continent, and the water mass, the ecoregion changed from 7 to 5 completely. And then on the Barents Sea shelf, it also changed to the different ecoregion completely. And the Atlantic water part, and they changed to, so we named it shift the events, and then analyze what's happening there. So here's, bottom is the parameter used for the classification, the 2, SST and SSS as a sample I just showing up here. So for example, the shift event 1 and 2 ecoregions distinguish between the 2 ecoregions by the SST clearly because they don't share the same range. But in this, the time from the 1950 to 2019, it jumps there. And in the same way, you can identify which one is the most important parameter that define this shift. And for example, Atlantic the water, SST, for surface SST does not change much. It shares the same range yet, but when you see the SSS, it's a totally different range. And then you can also add other parameters, which I don't show today, but shift event 1 and 2, for example, SST and short radiation is quite important to define. And then Atlantic water and surface salinity mixed layer depths are quite important. So you can pin down to what the environment change is most important to define those equation shifts. And then another important things, I gave you the second objective of the study. It's the uncertainty. So because the nutrient, the primary production is quite uncertain, so we do not want to rely on those information to define the ecoregions. And then this is one sample case of this no SM, but each ecoregions, when you map the net primary production, which was not used for the classification, you see that it's relatively uniform over the ecoregion over time. Over time, this is very important. So we can define, see this ecoregion carrying the same environment from now to the future. So when you identify the ecoregion which may survive in the future, and largely now, somewhere in the tiny part of the Arctic Ocean, you go there to observe what's going on there. That may be the largest ecosystem you will see in the future. So that's the way, I think, how to minimize the uncertainty from this CMIP 6 models. So this is a summary. So as you suspect, when you see this time series changing very abruptly between 2015 and 2017, this is associated with the CS concentration, of course. And then for the time series, sea ice, this is the CMIP 6 and 5, the model ensemble CS, the extent, the time series from the other study. And then from this, the projections, sea ice extent becomes quite small by the 2050, right? And then even when there's a very abrupt, the constant reduction of sea ice extent, the ecoregion stay quite strong to keep the similar, the area fraction at least. And then after ice goes, and then abrupt shift started. So that also tells the information that how many years we have to adapt ourselves, or to come up with the new idea about dynamical the management of Arctic Ocean ecosystem. So that's our conclusion. Thank you.
Thanks a lot, Tsuyoshi. Is there any question?
Well, then I can ask a question. So we learned this morning in this overview talk that the Arctic is prone to large changes in the coming years. So I was wondering whether or not these ecoregions that you do define in the modeling study have true meaning for people who work only with observational data or who are in fisheries. Are there overlaps? Have you checked with?
No. At this moment, ecoregion is defined as a static, as I showed at the very beginning, and then the resource, the monitoring, the management done over the static one. And then it's fine because, as I said, at least on the model, up to now, those ecoregions is very static. So last 50 years, for example, you can use this data to represent those equations. But if people are willing to use this information to project future, and this information at each equation is quite important, because now you can do this equation will go to where, so you can carry out this the information we get. So that's, I think, a message I have. Yeah.
So I do have a question. Okay, very quickly.
So when you work with some, you can also request the number of nodes that you are going to have at the end. And that number of nodes, has one impact on the accuracy of the results. Now, when you add more models, you are also going to have change in the number of nodes and the areas. So how do you think that we can solve that? Because I am also working with some and I have that question.
Yes, SOM is very sensitive to the definition of the map. Yeah. Yes. I don't have a clear answer yet. One is how you define the criteria, what is the best SOM. For example, when I plot the net primary production, that's a biotic parameter. But I want to make the biotic parameter as steady as much possible over the equation, because assumptions environment carries the same environment over the time. So maybe we can use that another the constraint to define what is the best.
Maybe it could be something to explore more during the lunch break.
Yeah. Okay. Thank you very much.
So, thank you. Now I would like to ask Sarah Weisberg to come to the front here. She will give a talk about resilience or regime shift in the Gulf of Maine food web during rapid warming. Welcome.
Thank you. Can you hear me okay? Yes, okay, good. All right. So good morning. My name is Sarah Weisberg, and I am a PhD candidate at Stony Brook University in New York, studying with Dr. Janet Nye and working with others who you see here. And much of my dissertation work focuses in the Gulf of Maine. So to orient you just briefly, the Gulf of Maine on this map is defined here by that yellow and black line. And as many of you probably know, the Gulf of Maine has been warming very rapidly over the last several decades. This is a figure showing the sea surface temperature trends in the Gulf of Maine as compared to the global average. So you see a pretty dramatic outpacing. And another way to look at this is the occurrence of marine heat wave events, which have dramatically spiked since 2010. So any black line on this figure is noted as a marine heat wave event. And really, almost all of 2012 was classified as a marine heat wave. And again, in 2021, pretty extreme. Yeah. So I guess unsurprisingly, perhaps, folks have been calling this a regime shift, have been pointing to a regime shift in the Gulf of Maine and other parts of the Northwest Atlantic. One other example I'll just talk about very briefly. A way that regime shifts have been classified is a step change in warm core ring births from the Gulf Stream. So here you see the annual average number of warm core ring births stepping up around 2,000. But most of these examples of regime shift have been described like this one in terms of the physical oceanography. And my question is, we know that ecological systems are resilient, and so, and don't respond linearly or instantaneously. Right? So when we think of the Gulf of Maine food web as a whole, what evidence do we have for regime shift over those several decades? And relatedly, what's the resilience of the system in that period? Has it changed? And I should point out that in the system, I show you these cartoons of some of the kind of canonical or charismatic players in the Gulf of Maine. And of course, we have our lobster, which has increased since the 80s, cod, which has declined, and there's been other sort of species-level changes. But species-level changes don't tell us about the food web as a whole, right? And again, there can be resilience or stickiness within a food web not seen at the species level. And I do want to take just a moment to define what I mean by resilience, because resilience gets used, I think, a lot of times in a lot of different ways by different folks. So what I mean is really kind of that classic Sheffer example or framework where you think about a system as a ball sitting in a well or a basin, and in order to shift, the ball has to cross over a threshold into a new basin or a new stable state. And so the same system can occur in multiple states, and those different states can have variable resilience. So in this cartoon, why do I keep doing that? This system over here, if the ball were over here, it would be in a deeper well, and therefore it would be harder to shift out of that state. Thus, the latter, the one on the left, would be more resilient. Okay, so I said I was going to talk about the Gulf of Maine as a food web. How do I do that? I built a model of the Gulf of Maine food web in RPath, which is an R-based implementation of the EcoPath with EcoSim mass balance modeling algorithms. So this static version of the food web is parameterized for the early 1980s and has 56 different groups in it. Some of them are single species, like cod, some are multi-species functional groups. And I'm using this to think about resilience as derived from trophic flow and quantifying such resilience using ecological network analysis. So one of the metrics in ecological network analysis is an efficiency metric, which you can think about as sort of the streamlining of trophic flow or mass flow. And to illustrate that here, we have the same food web, so the same nodes, and even the same wirings, the same predator-prey interactions, but a different weighting of flow. So on the left-hand side, you see there's thicker arrows in one side of the web, meaning the mass is moving in a more streamlined way. You can think about this as sort of a faster assembly line or a supply chain with only a few players in it. Right, that's an efficient system, but it's less resilient insofar as if you cut or disrupt one of those connections, the whole system is more likely to collapse. And I think we've seen that during COVID in a variety of supply chain ways. Okay, so going back to my food web, I can quantify again this efficiency metric on a scale of 0 to 100, and this scores at a 36%. Just trust me on that. Now, of course, I'm giving you thank you. I'm giving you that as a fixed number, but many of these parameters are uncertain. So to help estimate the uncertainty, I'm using something called EcoSense, in which I can generate not just one, but many iterations, sort of plausible versions of the same food web, cycle through, test each one. Turns out most of them are no good, so we throw them out, but end up with a suite of plausible parameterizations for that early 1980s food web. And based on that, what I saw is that there's a link between that efficiency score and some of what happens in the lower trophic levels. And I won't go into that too much, but just hold on to that thought, because then, after I explored that static food web, I wanted to see what's happened over time. And to do that, I fit to time series data. So I took that early 80s model and fit to a variety of time series using trawl survey and landings data, using copepod data, as well as some primary production data, all of which is made available to me by incredible people at NOAA. And then, additionally, I wanted to incorporate temperature directly. And I'll make a quick plug. This is one of the really awesome things about working in RPath, is that you can build in additional functionality over time. So I was working off, kind of cribbing off of work done by Maggie Heineken et al. To incorporate temperature-dependent bioenergetics into RPath simulations. So what this means is that you can set a consumption curve and a respiration curve for any groups of interest that are directly responsive to temperature, which is novel in those of you who have been in the EcoPath world before. So with all of that, I fit, again, to time series data. I'll show you just a few quick plots so you know I really did it. The dots here, the circles here, are the survey-based biomass estimates annually, and the line is my RPath model simulation. So changing around the initial parameters a bit such that the forward run matches the data as close as possible. These are some of the ones that I think are reasonably responsive. Some groups are not quite as responsive to overtime, but they never will be all perfect. So bottom line is I got to a place where I think the fit is at least decent, and then recalculated those ecological network metrics at each annual time step. And this is my result so far. So the orange here is a 5-year running mean of that relative efficiency score. And what I see when I look at this is I see a decline in efficiency. So you'll remember that's kind of an increase in resilience steadily until about 1999 or 2000. Then a steepening and an increase in efficiency or decrease in resilience until about 2010 or so, and then a pretty steep decline until 2015, followed by perhaps an increase again. So this shifting movement of the way that energy is moving through at least the modeled version of the food web. Okay, so who cares? And could this be really only a reflection of those lower trophic levels, as I quickly alluded to earlier? I think we have some hints that perhaps this is reflective not just of lower trophic level change, but rather of whole food web change, including the fact that in the ecosystem status report or state of the ecosystem report for New England, this is a figure from the Gulf of Maine. One of the findings has been that there's been a change in overall body condition as determined by the relationship between expected weight and length that have had this worsening in that same period that I saw a change in the system resilience. So that's one kind of hint, I think, or possible connection. And to further probe things in my modeled universe, I did a PCA analysis just of any groups that were trophic level 3 and above. So it's kind of cutting out the bottom of the food web, essentially. And looking at it here on the biplot, we see that the 80s and early 90s are clustering together, followed by a shift in the early 2000s. Again, something changing perhaps in 2015, and a return maybe to that early 2000s state in more recent years. I'm still exploring this further, but I did also want to look at the loadings values over time, and to kind of essentially to visualize this differently, and was intrigued that you see the same kind of almost wave-like pattern, or especially on the second principal component. And you also see these two sort of low values, these two pretty sharp inflection points in the time series. And so just to briefly look at a comparison between some of the different analyses, some of the different metrics, I put it together in a very simple table, looking at the year of that low point, the low inflection point, for each of those three time series, modeled time series. And I do indeed see two low points, one in the early 2000s, one in the mid-2010s. What stands out to me here is that the relative efficiency metric perhaps leads some of those upper trophic level trends by a year or two. And again, this is preliminary, but at least indicative that maybe we could use such a food web metric as one of our early warning signs among a suite of other indicators. Okay, so to sum up, in my analyses so far, we've seen these changes in calculated resilience in the Gulf of Maine food web, namely an increase up until 2000, followed by a decrease and a more recent increase. I think that's an indication that we may be in a new regime kind of from 2012 onwards in the food web, but it's a little bit too soon to tell based on what I've shown you here. And finally, that this network analysis approach hopefully can reveal some novel insights that explain other changes we're seeing and might be useful as an early warning sign of regime shift. So, of course, I have many people to thank, but 10 seconds left on that clock. So, briefly, thank you to Janet Knight, who's an incredible mentor, and Noah and Sea Grant for supporting my work. And if you have questions, you can reach out to me.
Thanks a lot, Sarah. Very inspiring. Also
you.
linking it to the network. Excellent. Is there any question? Yeah.
Yes, thanks a lot. So very interesting.
Thank you.
I was just wondering if it's maybe it's just a wording issue. So there seems to be a trade-off between efficiency and resilience in the food web. So for me, also working with the economist, this would be both terms which would be very positive in a way. Have you discussed about when communicating this to decision makers, if this is a real trade-off, or if maybe the efficiency could be termed in a different way? Because maybe it's more resilience you're heading for, but this, just if it's, I guess it's more wording, but...
Kind of, although I think philosophically there is a trade-off there. And I think we also do see it in economic systems. And is it possible to get the slides back up? Because I do have... No, it's okay. I'm one of those people who puts in backup slides. Because there's a good figure that I really like to point to that actually comes from a paper that was a collaboration between economists and ecologists thinking about this, which is trying to highlight that there is a tension, really fundamental tension between efficiency and resilience, so that in many systems, especially network systems, the more you streamline, the more vulnerable you are. And again, we see that in our, I think, day-to-day. I mean, a sad example I think of is the sort of what we saw with baby formula industry, last year, right? Essentially, right, that has become very efficient as an industry, but then you cut out a supplier and you have a huge social issue. So not to oversimplify things, but I think we do associate both with sort of have positive attributes, and yet there is a tension and a trade-off, and we have to kind of reconcile and perhaps try to find a good compromise. Sure.
Thank you. Also coming from the Stockholm Resilience Institute, I have had that discussion also. The next speaker is Bérengère Husson. He will be talking about non-additive, non-linear responses of a subarctic ecosystem to combine impact of fisheries and climate. Please come to the front.
Ooh, stairs. Ooh. Hi. Ooh. Yep, I forgot how it felt to see you in real life instead of behind the screen. Okay, this is the laser. So, my name is Bérengère Husson. I'm an ecosystem modeler at IMR here in Bergen, in always sunny Bergen, as we know now. And I'm going to talk to you about non-linear and non-additive responses in the Barents Sea, on which you already know many things now, and their combined impacts of fisheries and climate. Yeah. So we all know the drill. The ocean is going to warm, and the primary production and biomass is going to decrease in most ocean. And a frequent exception to that is the Arctic Ocean, where primary production is supposed to increase. And is it me? My hand. Oh, my hair. Sorry. I'm trying to push everything away. Whoop. Okay. Where was that saying? Yeah, so increase in biomass because of loss of sea ice, increasing the primary production season and triggering a longer productive season and higher biomasses, and also supplemented by northwest shift of species. The Barents Sea, you heard a lot about it this morning. It's a very already productive system that is sustaining a lot of fisheries, and it's also, according to global models, supposed to increase in the future in catches. But is it really true? Because those same ensemble models also tells us that this is where we have most often a high uncertainty due to differences between the models. And that's due to some local scale problems or dynamics that are not always taken into account in those models. And a recent review had also pinpointed that the past responses of the subarctic systems were very different according to the ecosystems. And that in the Barents Sea, there was actually uncertainty, as we heard earlier today, about whether the primary production is really increased or not. And of course, on top of that, you have the uncertainty that is linked to other drivers, like fisheries that can have synergistic effects and extreme events that can have stochastic effects on the ecosystem. Oops. So our questions were, how does climate impact the ecosystem processes and structure? And because we want to be able to predict better in the future, we were especially interested in the processes part. And then we wanted to know how this response to climate were changing when adding other pressures, so the interactions between climate and these other pressures. And not only fisheries, but also the uncertainty that we mentioned about the primary production. And then we wanted to see how does that affect the uncertainty and the predictability of the biomass. So we used an end-to-end model, Atlantis, for the Nordic and Barents Sea, which is a 3D result model with 57 species and has many, many processes involved, such as processes regulating the life cycle, the food web, and the migration or movements of the species. And we looked into a couple of processes here, and unfortunately I can't show everything to you today, but we are going to look at two of them. And then we combined the three drivers, and there are each of them three states that are very contrasted to be sure to see and to attribute the changes to which driver. This first driver is the temperature, which is forced by the original oceanographic model, so it's also forced with the advection and the currents in the model. And we choose to run the same year for the whole simulation, and we choose 3 years, 3 contrasted years, one a reference, a plus 0.4 degrees and a plus 0.6 degrees across the water column in average over the model domain. And then we have the fisheries driver, in which we have a reference state that is in business as usual, MSY fishing effort, and then contrasted scenarios at minus 25% and plus 50%. And for the growth, for the primary production, we modified the growth of the primary producer by plus 20%, of minus 20%, and that both englobes the uncertainty about the predictions, but also it's one of the parameters that is most, to which Atlantis is most sensitive, so it allows us to do kind of a parameterization uncertainty. We combine all of those drivers, and one scenario is one combination of each driver. And we compare the outputs to what we call the control scenario, which is the ones where you have all these drivers in the reference state, and that's what we call the response ratio. And that's what I'm going to use later. Something else that I'm going to use a lot is this combination of scenarios in which you change only the temperature, and that's what we call the temperature singular effect, or TSE, in the next slides. So let's look at the response first. Here you have the predation pressure and natural mortality, the mean response ratio as a function of temperature for different functional groups that each of them have several species in it. And first you can see that the responses are different from one group to another, but also that some of them are non-linear. And when you add other drivers and it changes the response. And it's not changing the response all the time the same way in all the groups. And sometimes it's changing the magnitude, and sometimes it's changing the shape. So there's obviously a lot of things to explore in there, and I don't have the time, and I'm just starting and probably never going to find the bottom of that. But I'm going to do a quick summary. So without surprises, the primary production scenarios are impacting bottom up and fisheries top down, but their effects are quickly dampened through the food web. So the changes in the response are quickly dampened, not so strong in the other levels. Another result is that across all the processes that I've looked into, it was mainly predation pressure and recruitment that were affected, and not so much growth or overlap with the other species. I'm going to skip this one. And for the biomasses now, so whether the processes impact the biomass or the biomass impact the processes is kind of a chicken and egg situation, but let's pretend that it's this way around. If you want to see how the combined effects of those pressures are affecting the biomass, you might start to think, okay, so it might be the additive effect of temperature plus the effect of fisheries plus the effect of primary production. And if that's the case, then your combined effect is approximately equivalent to those ones. Then you have what we call an additive effect. But we used the classification by Fu et al. In 2018 for the rest. So if you have a change that is larger in magnitude than the additive effect, it's called a synergistic effect, whether positive or negative. If it's lower in magnitude, it's dampened, and the ultimate kind of bad surprises, or good surprise, sorry, is that you were expecting something positive and it becomes negative, or you were expecting something negative and it becomes positive, and that's the antagonistic effects. So we can take all our combined scenarios and we look at the frequency of each category effect according to different temperature scenarios, and for prettiness purposes, we put a negative value to the changes that drive the biomass into a negative state, and positive value for a positive state. And we see three main things. First, that most of the time your effects are dampened, so that's what we were saying earlier. It's not as high as you would think, either not as low, but also not as high. You also see that with warming, you have an increase in the blue colors, so the increase of negative impacts, and a decrease of positive ones. And you have also an increase in bad surprises, like a negative synergism. So conditions that become even worse than you would have expected. And what does that mean in terms of changes in biomass? Well, here, if you're looking at the temperature alone and the response ratio distribution for each of those groups, so each of those groups have several species, so of course it's depending on the number of species, but you can see that the magnitude of response is increasing with the temperature, so your distribution, your range of your distribution is larger when you go to darker colors. And when you add all the combination, across all the scenarios, then you can see that it's even more spread. So somehow this is showing us that the uncertainty or the responses are going to be even more uncertain. So some take-home messages, and that's of course under the model assumptions, and we can discuss a lot about that. First, we saw that there are nonlinear response of the ecosystem processes to climate change, at least some of them. We saw that this response can change under the combined effect of several drivers, but we saw that it's quickly dampened through the system. But we also saw that this is not going to be so much the case if it's getting warmer. So all in all, we saw that it's increasing the uncertainty around the real trajectories of the biomass in the Barents Sea under a warmer climate. And going further very quickly, of course, this is calling for global and regional models and more comparison between models at different scales. And my question to you, and what I hope to try to understand through this session today and the other days, is according to those non-linear tipping points, shifting, regime shift, etc., how do actually we predict them? How much of it should we predict? And how do we handle the uncertainty and communicate it? That's it, thank you.
Thank you very much. Just a very quick question, otherwise we would need to move on. And I would urge you that maybe if you have a question that you talk to you after lunchtime. Okay. Thanks. Okay, now we move to the last speaker before the lunch break. And that's Brian McKenzie, talking about a regime shift in the southeast Greenland marine ecosystem. Brian.
Yes, thank you very much. So the presentation this afternoon, it's now after lunch, or almost after lunch. It's a collaboration with several colleagues, as you can see here. I should say right at the outstart, I'm not an expert in marine mammal ecology. That person at the start, Mads Peter Heider Jorgensen, is that. So I'm just giving some input on some of the fish and some of the oceanographic variables. Okay, so the work is actually part of a EU project called EcoTip, investigating ecological tipping cascades in the Arctic seas, which is a EU project. And we're also contributing some of the results and findings into the ICES working group on integrated ecosystem assessment of the Greenland Sea. So in this project, our work has mainly been focusing on the ice temperature conditions and how those changes, or how the changes in the ice and the temperature is affecting marine mammals, fish, and trophic interactions. Our main hypotheses are that warming in the last 1 or 2 decades is actually detectable in this region. And the region I'm mainly focusing on is mainly in the southeast Greenland area, Bérengère Sea. But what's happening there, I'll show it in a few minutes, is very closely connected to what is actually happening much farther north. So we're also wondering whether some of these warming impacts are having some effects on the upper trophic levels, especially marine mammals. Well, before I go too much farther, I want to give a little bit of background about what coastal or shelf sea ice actually does in the area. What is its function? Well, it provides habitat, direct habitat for species, feeding, breeding, resting. For species such as walruses, some fish species like the polar cod shown there. Also seals and polar bears. It also has a blockage effect. So the ice that I'm talking about is not the sort of permanent ice, it's sort of drift ice which comes, drifts into the area from the north. So it's a seasonal influx of ice which comes in, and it can actually block sort of access to the coastal zone or the shelf area, or block access to it by open water species, especially air-breathing species. And of course, it has some impact on temperature. Having blocks of ice in water, as you know, keeps it cold. So it helps keep local temperatures low. It provides, in that way, cold water habitat for cold adapted species living in the water. So we have used 2 main sources of data, or kinds of data, in this investigation. One is based on satellite imagery. You can see an image here from August 20th, 2015. And from the satellite imagery, we can get some estimates of the ice transport from up north coming down along the coast. We also have access to some historical ice extent data from the area going back 200 years. So these are data which were collected along the coast, especially up the West Greenland coast, by historical accounts and reports. So these were people that were living in the area or visiting in the area, and would estimate or record, in fact, how far the drift ice would come down the southeast coast, come around, and actually start going, being drifted, evected farther up the west coast. So these records go back. They're available pretty much on a monthly basis, at least in the summertime. And this is the August data that I'm showing here on this panel. And I think you can see that there's a lot of year-to-year variability. It's some years there's a lot, and other years there's basically nothing or very little. You can see some periods when there was a lot, and some periods when there wasn't very much. And especially in the last 20 years, we're seeing quite a change. So basically, what we're seeing is that the coastal zone is more or less becoming ice-free, at least in the summer, in the southeast region of Greenland. We've actually applied some regime shift detection method to the time series, and that shows us that there actually has been some changes. So this is the summer, sort of June, July, August index for the entire summer. And you can see there's a long period here where there's some year-to-year variability, but no real regime shifts or changes. And then in 1930, roughly, there was a drop, meaning conditions were a little bit milder, not as much ice. You can see a lot of years when there wasn't very much. And then it came back up, got a bit colder again. It was stable for about 20 or 30 years. And then in 2003, another drop. So this most recent drop that we see here seems to be unique, at least in this 200-year period. There's no other such long event during this period with such low mean ice cover. It's also kind of unique in another perspective, and that's because it's consistently low. If you look back here in this previous low period, there was a lot of years when there was some actually quite high ice events, almost every second year or every third year or so. There's quite regular events. So that would have some impact on the biology. On the other hand, in this last 20-year period, we hardly see any of these strong ice events. It's basically consistently low. So basically, not only there's been a change in the overall level, but also a change in the variability in the most recent time period. Right. As I mentioned before, we have looked at the satellite imagery for ice export. And this is a measure of the volume of ice exported from the Fram Strait coming from the north. And you can see a drop-off here also in the early 2000s. There's a decline in the area of ice coming, but not yet evident as a regime shift. And we think that, in fact, the ice volume is a better indicator of how much ice is exported because the volume accounts for the thickness of the ice as well. So we see two kinds of indicators of a change in the ice conditions, and probably this export is affecting what we're seeing farther south. It's affecting temperatures. We have looked at temperatures in these two boxes, and we also have some data from here. I'll show these northern ones first. So up here, not too much changing. It's pretty stable still, so there's a lot of ice still in the winter time and in the summer coming out. But farther south, the temperature is starting to go up, at least based on these data. It's having some impact on the biota. So we've mainly been looking at the marine mammals. So these are estimates. Well, they're not estimates, they're actually catch data or hunt data by the local people. So these are the catches or the hunts of different species. And if we focus on the top two, these are sort of cold-adapted species, narwhals and walrus. Both ones have been declining also since around 2000. On the other hand, the catches of other more warm-adapted or perhaps temperate or a little bit more boreal species, these have been increasing a lot. Dolphins, minke whales, pilot whales, and killer whales. So basically, the warm-adapted species seem to be becoming more common, or at least migrating into the area closer. We're also seeing some changes in some fish distributions. Mackerel became very abundant. The mackerel population in the Northeast Atlantic spread from the continental shelf, the shelf break area, initially out towards Faroes, Iceland, and then all the way over here in the Denmark Strait, northern Erminger Sea area. Mackerel previously has not been seen in this area and was certainly not available in commercially exploitable quantities. And in fact, for some years, there was a fishery here on the order of tens of thousands of tons. So this species has come in partly because of the mackerel population itself expanding and its biomass increasing, and partly because of increases in temperature and changes in the conditions here. Another species which come in is in fact a predator of this one. Another migratory species, bluefin tuna, has also come in, and the first time we saw it there was in 2012 because it was actually caught as bycatch in the mackerel fisheries. Bluefin tuna, as I say, are predators of mackerel, so they were probably reacting to the change in the distribution of the mackerel, as well as the change in the temperature, which has also been increasing. So species like mackerel and bluefin tuna have arrived. They haven't been present before 2012. And this has consequences on the food web. These predators, especially fin whales and humpback whales, they're consuming hundreds of thousands of tons of fish, krill, and squid. So the main predation impacts are from those two, but the other ones are also eating as well. So we're seeing changes in the ecosystem. Ice conditions are unlike anything seen in the last 200 years. A tipping element, coastal pack ice, has passed its tipping point. It's less supply from the north, and local ice is melting at a faster rate. This is probably not going to come back again unless we have quite a severe series of cold years. A future cooling event, it might get a bit colder perhaps, but it may not be enough to cause the ice to come back. So a tipping cascade, we think it's underway, changes in species distributions, trophic flows, and food web. So this area and event, we think it's perhaps a forerunner of what could be expected even farther north in the Arctic Ocean. Some conclusions: major changes occurring in the region, especially in the last 10 years, on shelf, shelf break, and beyond the shelf. We see it in terms of the hydrography, we see it at fish at different trophic levels, and also for the marine mammals. So there are impacts on ecosystem functioning, many of which we still have to investigate, and there will likely be impacts on fisheries and ecosystem management. And I'll stop there, and thank you for your attention.
Thank you, Brian. You have a question to Brian? Yes?
Thanks, Brian, for the presentation. I was curious about the catch, the hunting catch data.
Yes.
On to what degree it was reflecting changes in the availability of the different whale species, or it was reflecting changes in hunting practices, maybe a decline in narwhal pushed the hunters to go to other species, or the change in the ice condition offered other opportunities for hunting. Could you elaborate on that?
Yes. I think the people are basically opportunistic in the sense that they more or less take whatever is available to them. So historically, the ice was pretty much blocking a lot of access to the coastal zone of some of these other species that are now basically coming into their hunting area, basically. So that's the main mechanism that we think is behind it. So they don't really have, I don't think they're targeting so much particular species. And some of the species have not actually had quotas or regulations. So in that way, it's quite a different setup compared to commercial fishing operation and commercial fish practices. Yeah.
Okay, thank you. Then I would like to thank for this morning all the speakers for the excellent presentations and also the questionnaires. Thank you very much. And we will reconvene after the lunch break at 1:30. And I would like to ask the speakers who are the first three for the after lunch, please come up a bit earlier so we can mic you up. Have a nice and networking lunch. See you.
Okay. No? Yeah? Can you hear me? Yes. Okay, guys, welcome back from lunch. I guess a lot of people will arrive a bit late, but we have to move on with the program. So for all the speakers of this session, remember to go before to get the mic before your presentation, and that you have 12 minutes plus 3 minutes of question. So the next speaker will be Benjamin Planck.
Okay, so thanks to all of you who have made it on time after lunch, and welcome to the latecomers who will flow, I guess. So I will talk about a methodological topic, which is the detection of critical transitions. So are they spurious or not spurious? And this work, I've prepared this presentation together with Lucie Butet and Saskia Otto. But the whole work was actually part of a more general group that conducted a series of workshops within ICs from 2018 to 21, and it was workshops on integrated trend analysis. And the purpose of these workshops was to actually evaluate the strengths and the weaknesses of a number of trend analysis methods that were used in the ICS framework to support integrated ecosystem assessment. So I just show one short fraction of these workshops, but I encourage, if you have the time and the interest, to access these workshops at ics.dk. So the approach we took is actually borrowed from biomedical research, and it's the analysis of the specificity of diagnostics. So I will explain how that works. So you start with a question. So in biomedical research, we can ask the question, okay, is someone, for example, infected by COVID or not? So do you have the disease or do you not have the disease? And to answer that question, you need a diagnostic tool. So you can have very non-specific diagnostic tool, like a thermometer that will measure the temperature of the patient, or much more specific diagnostic tools like the antigenic test that you see on the right. And then once you get the result from the diagnostic tool, it can say, okay, there is evidence for disease according to this diagnostic. And you ask, okay, can I trust that evidence? Okay, so specificity is actually the capacity of the diagnostic to identify or to diagnostic the disease when it's truly there. So in other words, it's 1 minus what we call the false positive rate. And the false positive rate is when you have a diagnostic that gives evidence for the disease, but in fact, the disease is not present. Okay, so we can apply the same thing to look at critical transitions, and that's what I'm going to talk about today. So again, you're asking the question, is there a critical transition or no critical transition? You need a diagnostic tool to detect your critical transition, and then you get evidence for critical transition, and you ask yourself, okay, can I trust that evidence? So in other words, what is the rate of false positive that gives evidence for critical transition when there is in fact no critical transition? Okay, so I'll move on to the critical transition. We've seen this type of graph already earlier today. So typically, you have this marble metaphor with two basins that symbolize different stable states of the system. And the tipping point is in the middle, where you cross the line, you move from one stable state to the other. And this is the critical transition. And the nice thing about this metaphor is that you can actually translate it into a 2D diagram that looks like this, where you have the system conditions on the x-axis and the system state, so it was the marble position on the y-axis. And when you have a critical transition, you have something that resembles this shape here, where you have one basin is symbolized by one line, and the other basin is symbolized by the other line. And there is a break in between these two, and that is where the critical transition is taking place. And a few years ago, a method was proposed called integrated resilience analysis, which is based on the analysis of this diagram, But the cool thing that this method is doing is moving from this theoretical diagram to using empirical data to try and test that. So here is the result that is presented in the original paper, and it shows, so it's different years of observations, and for each year you can describe the conditions and you can describe the ecosystem state, and you try to relate one to the other, okay, and see if you can identify a critical transition. So it's working in different steps. The first step is to summarize all your environmental conditions in one univariate time series. So often this is done with a reduction dimension like PCA. The second step is to do the same thing, but for the ecosystem state, where you summarize information from the ecosystem into a univariate time series using a PCA. And the third step, which is the really important one for critical transition, is you try to model the relationship between the two with models that are either continuous or discontinuous. And if the best model is a discontinuous model, then you say that you have a critical transition, okay? And here they've used in this paper GAMS, so general additive models, or T-GAMS, which is threshold GAMS, which is these discontinuous models. Okay, so, okay, and there's a fourth step, but I won't talk about this, which is the resilience assessment itself. So what we did is, I will show you the results for the Barents Sea. We took the data for the Barents Sea. We injected that data into the integrated resilience analysis workflow and got the results out, okay? And you will see that we find evidence for a critical transition. But on the side, we had a control model where we generated a lot of time series that looked like the observation time series, but that were all independent from each other and in which there was no critical transition. So these are our negative control. Then we pass them through the IRA workflow and look at the outputs. And if we find that the method find a critical transition, then it's a false positive, okay? So we look at the false positive rate. Of course, the lower, the better. So here, just to illustrate the way we generated the time series, the control time series, on the left are 3 time series that we had in our original observation data sets. And on the right are simulated data. And these simulated data, they are random, but they have the same mean, the same variance, the same autocorrelation, the same trend as the original time series, but they're all independent from each other, and they don't contain a critical transition, okay, or a shift in the individual time series. So if there is a critical transition in the system as a whole, it happens by chance. Okay, so the results on the observational data for the Barents Sea looks like this. So it's not exactly the same plot as what you've seen earlier, which was taken from the original article, but you see a similar pattern where we have actually a model that tracks a relationship between environmental conditions and ecosystem state at the top here for a while, and then it breaks and moves to another relationship later on in the time period. So that's how it looks on the observations. Now, how does it look on the control time series? And we did that 100 times, but I will just show you 5 extra plots for illustration. And here are the 5 others. And on the 5 others, what you can see, so they're all different from each other, but they all have the similar pattern that you have a time period that corresponds to one fit and another time period that corresponds to another fit. So a critical transition has been identified on all this, okay? So to look a little bit more, because it's difficult to analyze these plots as a whole, we looked at the different steps, and I have 3 minutes to go, but I will guide you through that. So first, we looked at the first step of this analysis, which was to summarize all the environmental data into one dimension and ask, how does that perform in our observations versus our controls? And when you run a PCA, the first thing you look at is the percentage of variance that you can explain with your first principal component. If that is really high, you usually say, okay, then I have a good summary of my data with that univariate time series. So the higher the variance, the better. So what you see on this graph is the result is the dashed line here. So it says about 70% of the variance of the original time series was explained by the first principal component. And this histogram here is the controls. So on the controls, you usually, on random data series, you get quite good percentage of variance explained, but they're always lower than on the observational data. So here, the methods on the observational data seems to work fairly well, at least better than what we would expect from random data. So now that you've followed that, I will do exactly the same thing, but this time for the biological data that we've used. And here we have a quite different picture, because when we summarize the biological data, we can explain around 33% of the variance. But when we summarize random data, we get about the same thing. So it means that these data are not more related to each other than random data would be. And that's quite worrying. That means we are trying to make a summary of something that's hard to summarize. So it's not performing very well here. So if you go back to that plot, it means what does that really mean, what we're following on this y-axis? What is the meaning of that? And finally, we look at the third step, which is the fitting of GAMs and T-GAMs and comparison of them. Okay, so when we fit the GAMs, so the models without the critical transition, what we find is that that model can explain around 30% of the variance, but the controls also explain as much or more of that. So when you have random data, you always explain a relatively large amount of the variance with a GAM model. If we move to the T-GAM, what we see now is with the T-GAM, we explain almost 70% of the variance, which is much higher than the 30% that we had earlier. But when we look at the controls, they explain on average 85% of the variance of random data sets. And in addition to that, on the controls, on all the controls, the 100 controls that we did, the T-GAMs, they always outperformed the GAMs. So we always detected a regime shift or a critical transition, I would say. So the conclusion, in my 10 seconds left, is that at least for the Barents Sea, the specificity of the integrated resilience analysis method to detect the critical transition is very low. In fact, it's null, the specificity, because we had 100% false positive rate. So it's not a method that is applicable. It doesn't mean there was no critical transition, but it means that the method is not capable of detecting it, because it's detecting critical transitions all the time. So what we have is a kind of thermometer and not antigen test. Something that every time something is changing in the data series, whoop, we identify a critical transition. So we would need to test that on other case studies or other regions, and that we did in this workshop that I mentioned. And not all of the regions are as bad as an example as what I showed, but they all have serious issues, I would say. But the conclusion is more general, is that any method, and that's not specific to the integrated resilience analysis, any methods that is used to detect critical transition should be systematically assessed against controls, as I've proposed today. Thank you very much for your attention.
So are there questions for Benjamin? If yes, please come here on the front. And don't be shy, yes.
Oh, it was so fast, so I didn't catch every story behind. But when you generate a control based on the mathematical model, what is the guarantee those signals not including the critical transition? Is there any constraint not to produce?
Yeah, these signals are generated through a trend and autoregressive process. So there is no mechanism in there that simulates a critical transition. What can happen, of course, is that the result looks like a critical transition. But in this case, all the results look like a critical transition. And this is what is worrying. If we had 5% of the results looking like a critical transition when we haven't put it in the first place, then we could say, okay, we have a 5% error rate, and that's acceptable.
Okay, then another question is, if it were the case, do you have any simple, like an autoregression model that can include, reproduce the critical transition as a another type of set of control.
Yeah, so what we did here is the specificity analysis. So we are looking for the false positive, but we could have done, and this we haven't done, the false negative. That is, you create time series or ensemble time series with a critical transition, and you look at how often you miss these. And that gives you an idea of also of how performant your method is. So that's the other part of the analysis, which I haven't presented here. Yeah.
Ah, okay, but you did. Okay,
yeah.
Thank you.
Okay, the time is finished. Thank you very much, Benjamin. So the next speaker is Ernesto Villarino. Please come.
Okay, thank you for coming over. My name is Ernesto Villarino. I am a postdoc at ASTI doing species distributions linked to environmental change. And today it is Ocean Regime Shift and Biodiversity Turnover in the Bay of Biscay by Jiaying Chen that unfortunately couldn't make it here last minute. So yeah, here I am. This is a collaborative effort with a bunch of people involved, most of us from ASTI, and the work is framed into the Naturklima project, which can be considered the Basque country's largest climate action taken in terms of resilience, involving several actors at the interface of science, communication, and governance. It looks like we're doing great at breaking records and altering the physical, chemical, and biological properties of the ocean. In fact, we are seeing already warming velocities of 0.2 and 0.3 degrees in vast areas of the North Atlantic. So this sustained warming, together with a decrease in oxygen and increased acidification, will lead to a decline in primary productivity in most of the areas. So this will have important implications in marine biodiversity, particularly in biodiversity redistributions. Species might respond to ocean warming in different ways. For example, when environmental conditions fall outside the species' tolerant ranges, the species might adapt either through physiological adjustments or with genetic modifications that might require more time. But when environmental change is too strong, the species would either move polewards or deeper in the water column, trying to look for colder waters to sort of accommodate their climatic niches. This, if the species can move, if not, two options: adapt or extinct. But other than species redistributions, the body size reduction has been shown to be another universal response, gaining more and more attention in the scientific community. So today in this talk, I will focus on some of the responses applied in the Bay of Biscay. So trying to understand the responses and to face other global ocean challenges, the Marine Observatory of Climate Change in the Bay of Biscay was built in 2020. And this is a locally focused but globally relevant entity trying to improve the resilience capacity of coastal ecosystems in the Bay of Biscay, as well as the lifestyle of the people that depend on these ecosystems. Within this context, we integrated monitoring to detect large-scale shifts in response to changing environmental conditions. And to do that, we made use of a bunch of indicators from physics to biology. Today, I will focus on a few of them just for the sake of brevity. So to achieve this, we use the existing resources at ASTI, including a bunch of monitoring programs targeting weather forecast, hydrography surveys, providing advice, contributing to many stock assessment groups at ICES, or checking the ecological status of coastal systems. So taken together, we analyze 87 time series using a bunch of observations and including 19 indicators across the Bay of Biscay. And to do that, we use generalized additive models that are quite good when we have irregular data at different sites and complex seasonal cycles. So we constructed the GAMs that accounted for linear trends over time, cyclical fluctuations within a year, and temporal correlations. For those variables that we had data at different sites, we use mixed model GAMs, including the site as a random effect. So by doing that, we found an important sea level increase in the area with an increase of 3 centimeters per decade starting in the 90s. We also looked to ocean warming trends by looking to the Aquarium of San Sebastian data and found an important warming velocity of 0.2 degrees per decade, as well as a slight increase over time down to 100 meters. So these physical changes, of course, were well tracked by the biological communities, as seen in an earlier spawning of anchovy, earlier arrival of albacore, or a northward shift in the Atlantic mackerel distributions. However, very few studies have addressed ocean warming impact at community level, and a good way to do that is the Community Temperature Index, or the CDI. That it is a quite simple habitat metrics that sort of synthesizes a bunch of information in a given number as it calculates the mean thermal affinity of a community, including the species thermal threshold, as a function of the relative abundances. So under an ocean warming scenario, one might expect the CDI to increase over time if the communities are to track their climatic niches. We can go one step further and dig into the underlying ecological processes driving variations in CDI over time. And we can do that by checking if those changes are due to an increase or decrease in the abundance of cold or warm species. The good news of CDI is that it can be applied across different systems and groups. For example, here we analyze temporal patterns of community assembly in copepods using time series data across the North Atlantic and Mediterranean Sea, and we found that the species thermal thresholds on one hand and the velocity of ocean warming in the other were key factors setting temporal patterns of plankton community assembly. So basically, copepods at those sites were tracking their climatic niches with the tempo dictated by ocean warming. Coming back to our study area, here I showed the CDI dynamics for a quite nice community of soft and hard bottom bentos. And you see a slight increase over time in both CDI and local temperatures. If we look to the drivers, it looks like the communities are changing towards warmer, particularly warmer and to some extent colder species, but those changes in the community cannot be only linked to an ocean warming trends, as we found quite weak correlations between the CDI and local temperatures. This study contributes to a wider effort where we put together and analyze CDI dynamics over Europe, including different regions and taxa, including zooplankton, benthic communities, crustacean, mollusk, and fish. And on the right-hand side, you can see a quite important warming going on in Europe over the last 40 years. And with the numbers, the different case studies where we took the data from. And on the left, the CDI changes over time in terms of degrees per decade. So it looks like the CDI is mirroring those dynamics seen in ocean warming as seen in positive CDI changes in most of the cases. And from those, almost the half were significant. When we look to the drivers, it appears that the biological communities altogether are showing a quite straightforward response to ocean warming, particularly with a domination of tropicalization, but also followed by a deborealization or a decrease in cold species. We also look to body size changes patterns over time, and to do that we make use of existing monitoring programs at ASTI, including Bioman and Juvena. And we did that looking to weight at age using mean annual data. And we found that body size decreased in all size classes, particularly in anchovy over the last years. So let me stress out here that the pattern observed might be wider than expected only from warming. So we believe that other factors other than warming might be also playing a role, including fishing pressure or pollution or density dependence processes. And let me finish the talk bringing to the table a recent paper out in Ecological Indicators by Chust and colleagues that they found contrasting responses to ocean warming in the spawning latitude and timing of horse mackerel and Atlantic mackerel over the Northeast Atlantic in the last 30 years. And using GAM with the latitudinal distribution as a function of the timing, they found that the Atlantic mackerel has shifted northward in warmer areas at a quite important rate, while the horse mackerel looks to spawn earlier in time as a response to ocean warming. So these contrasting patterns seems to be related to the narrow thermal reproductive niche or horse mackerel that sort of is doing to have a tight coupling between timing of spawning and location. But Atlantic mackerel seems to behave more freestyle, spawning synchronously across all latitudes. Well, taken together, using a bunch of monitoring programs in the Bay of Biscay, we have found strong ocean warming, as well as a steady sea level rise that is not only impacting the benthic assemblage or structure in the communities, but also fish spawning and weight. In fact, weight at age for anchovy and sardine decreased since the beginning of the century. In the Northeast Atlantic, the horse mackerel spawned earlier, while Atlantic mackerel did shift northward their populations. So we definitely think that estimating accurate rates of ocean warming, sea level rise, and biodiversity changes can be key to define adaptation measures, minimize impacts, and take informed decisions. So I would like to acknowledge the following bodies for providing the data or putting the money. Thank you.
Are there questions for Ernesto? Someone? No? Okay, then maybe I have a question.
Okay.
If I understand correctly, you measure this mean community temperature in the benthos or also in all the species of the community? In all the species?
In all the species, yeah.
Of the community?
Yeah.
Okay. And when you say that it increased like the tropicalization, like more species from the south are coming in, you mean? And you say that part is the deborealization. What do you mean with deborealization? I don't know.
Deborealization is a decrease in the cold species. So both processes are linked to ocean warming, right?
Okay. So they kind of become less or they move farther?
Yeah, the abundance decreases. But this is a bit surprising result for benthos because they have short dispersal scales. So one might think that the arrival of warm or cold species might be done during their planktonic phase. Otherwise, this result is quite unexpected.
Okay. Thank you very much.
Welcome.
Okay. The next speaker is Anna Heinz.
Okay. Hello, my name is Hannah Haynes, and today I'm going to present my master's thesis entitled Investigating the Evidence of a Regime Shift in the Norwegian Sea, which I'm currently working on at the Institute of Marine Research in Tromsø, Norway, with Benjamin Planck and Lucie Butet. So first of all, what is a regime shift? So there are many different definitions, but here I'm going to define it as a sudden and abrupt shift in community structure on several trophic levels, leading to the rapid reconfiguration of an ecosystem which is persistent through time. Furthermore, during this talk, I will distinguish change points from regime shifts, which for me at least refer to data points in univariate time series which could potentially constitute regime shifts if they are combined with other concurrent change points in related time series. So beyond these definitions comes the problem of detecting these phenomena. So there are many different methods. Some have univariate or multivariate approaches. Some are based on changes in mean, variance, or trend. Some methods are purely descriptive, while others are statistical. Indeed, with over 40 different methods, there is no golden method for regime shift detection. And too often, these methods are applied to all types of time series without first checking their suitability or performance. So one of the motivations for my master's thesis was that the regime shifts are now at the forefront of ecological research, and with more and more papers published every year, among which is this paper, which was published last year, which identifies a previously missed regime shift in the Norwegian Sea. As such, during my thesis, we wished to investigate the evidence of a regime shift in the Norwegian Sea, with a particular focus on the performance of different regime shift detection methods, as too often these methods find regime shifts whether they are present in the data or not. So for this project, I had access to over 30 different physical and ecological time series, all relating to the Norwegian Sea, among which I've selected 6 to present today, so 3 abiotic and 3 biotic time series, which all have different lengths, as you can see, and different dynamics. Some are very noisy, like the NO and the temperature time series, whereas others have smoother fluctuations, like the Arctic water and the herring biomass time series. When looking at these time series, we can imagine there being a change point in the herring biomass time series in 1965. But in order to confirm or reject this and other potential change points, I turned to statistical tests. So, go back. So I applied 2 different widely used regime shift detection methods, which both have corresponding R packages, after having preliminarily transformed the data with a robust normalization technique called omnibus normalization, as these methods call for normal data. And so here in purple and in yellow are arrows that indicate the years where respectively the Anthropogenic and the STARS methods found regime shifts. And as you can see that these tests give rather conflicting results, especially for the NO and the herring biomass time series. So while these 2 methods have different underlying assumptions about regime shifts, this still begs the question, which test is actually right? So in order to answer this question, we must first understand the possible errors of these types of tests. So all of these tests attempt to answer the question, is there a regime shift? And either the test responds yes or no. However, we should not blindly trust this, and in each case we have to imagine what is actually happening in reality. So first, in the case where there is in fact a regime shift, the test would have been right in one instance and wrong in the other. And this type of error is called a false negative. The same can be said in the case where there isn't a regime shift. However, this type of error is called a false positive. Of these 2 errors, I'm going to concentrate on the false positive rate, or in other words, the number of times a test says there is a regime shift when in fact there isn't. So logically, the confidence we can have in these tests is greater the fewer false positives there are. So how can we test the false positive rate? So to do this, we can use surrogate time series, which are simulated time series that can serve the same trend and autoregressive processes as the original time series, but not any change points that may have been present in the original time series. As an example, I've taken the herring biomass time series, which before generating the surrogates needed to be detrended and normalized, with the same method that I mentioned previously. It is important to stress that by design, these surrogates have no change points, and thus any part of these time series that resemble change points can in fact simply be explained by autoregressive processes. So in order to use this technique to determine the number of false positives, 1,000 surrogates were generated, and the tests were applied on each, and the false positive rate was deduced from the number of surrogates for which the test found a regime shift. So as such, they serve as a baseline for the null hypothesis: there is no regime shift. So all of my results are going to be presented in the same manner, in the form of bar charts, where the blue corresponds to the proportion of false positives, or in other words, the number of surrogates for which change points were detected. And conversely, the grey corresponds to the true negatives, So if a test performs perfectly, we would expect 1,000 true negative results, or 1,000 response to the question, is there a regime shift? So no. However, we accept a 5% error rate. So first of all, I tested the Untitled method, which is a modeling approach that was used in the paper that I mentioned previously. So this method attempts to fit 8 different models to the data, 4 without a change point and 4 with a change point. And this function also associates BIC scores to each model, which allows you to pick the best model. So as surrogates contain no change points, the criterion to detect a test error was that the best model was one with a change point. So in the results, immediately you can see that none of the 6 variables that I presented previously have an error rate below 5%. And in fact, they can reach 65% in the case of the zooplankton time series. It is thus easy to conclude that for these types of time series at least, this method has a very low performance. So after the Untitled, I investigated the STARS method, which stands for Sequential T-Test Analysis of Regime Shifts, and is very popular in ecological research, and it calculates for each point in the time series a regime shift index, which is used to determine whether or not the current point is different in a different regime from previous points. So p-values are generated and only significant change points are returned. As such, that's the criterion I used to evaluate it. And again, the results are quite clear, with false positive rates going from 22 to 100% this time, while most are above 80%, meaning that flipping a coin would certainly be better. However, both the Untitled and the STARS methods are univariate and thus take the time series one at a time, which, considering the definition of a regime shift, which calls for multiple simultaneous changes across different compartments, seems like an oversight. So as such, I wanted to test a multivariate method to see whether or not it would perform better and have a high enough performance in order for me to conclude whether or not there was a regime shift in the Norwegian Sea. So for this, I turned to chronological clustering, which is a modified clustering method which only allows sequential data points to be joined, as such breaking the time series into different time periods. So to test this method, I added a few more time series and performed 3 different groupings, 1 abiotic and 1 biotic grouping and a mixed grouping. So as clustering methods will always find a way to split the data, the optimal number of clusters was confirmed with a broken stick model. So if more than 1 cluster was significant, this suggests the presence of a regime shift in the multivariate surrogate time series, and as such, this principle is used to determine the number of false positives. So the results from this show that for one of the groupings, the mixed grouping, the error rate comes quite close to the acceptable 5% error rate. However, for the other 2, the regime shifts are too often detected still. So here again, it seems that chronological clustering falls into the trap of finding regime shifts when there are not. So as a general conclusion, and as to answer the question, is there a regime shift in the Norwegian Sea? We can only say that with a very high false positive rates for all tested methods here, which are consistent across all 32 time series that I tested and that I didn't present today, that it's impossible to conclude. We can neither confirm nor deny the presence of a regime shift in the Norwegian Sea, because all the methods tested here are inherently biased towards finding change points. These results are also in line with what my supervisor, Benjamin, presented for the IRA method earlier. These high error rates could be due to the fact that these methods were developed for much longer and regular time series. Unfortunately, these kinds of ideal time series are very rare in ecology. So finally, this is a work in progress, and there are many more methods to be tested, so hopefully one will be slightly better than the ones I presented today. So I leave you with this message for regime shift detection methods. So before concluding the presence of an ecological regime shift, it is essential to verify the used method's specificity, particularly relating to the time series employed, as these methods often have high false positive rates. Thank you for your attention.
So, are there questions for Anna?
I think it seemed like the last time series, which I think was herring, seemed to perform like the worst in most of your methods. It was most likely to have false positive. Was there anything that you could discern about which ones seemed to be the worst? Like, what about their time series might make them more likely to be bad? I mean, none of them are good, but.
Well, it kind of depends on the method. So the anthropogenic method uses the autoaggressive processes inside the method testing. So that would probably perform better for methods, or for time series where there's a lot of autocorrelation processes that are going on. And other methods, like the stars method, perhaps if they're noisy time series that go up and down a lot, it's probably more likely that they'll find regime shifts just in the noise.
Yeah, thanks for the nice presentation. Relatively simple question, maybe also to Benjamin Plonk. Is there actually any way forward now with all these methods not or detecting these false regime shifts? I mean, or is there maybe a possibility to incorporate mechanistic modeling also to come up with a method that can actually detect true regime shifts and not the false ones?
Well, it might be a bit above where I'm at the moment, but like I said, there are loads of more methods to be tested, so maybe one will be better. But yeah, maybe integrated modeling, something like that. I honestly, I don't know.
Thanks.
Are there other questions? There is still a bit of time. Maybe I have a question. Do you know why, or do you have an idea why in the last thing that you show about the regime shift with the clustering, like when you cluster together the abiotic and biotic variable, you had such a better results compared to than when you cluster separated?
Yeah, one of the theories that I have is because that cluster was a lot shorter, so the time series that they took were a lot shorter. So there's less possibility for regime shifts because the regime shifts can only be detected every 7 years, I think I put into the function. So you only have so many 7 year periods in the 20 years of time series. So it's less likely, because of the constraints of the length of the time series, that it finds regime shifts. So it might not necessarily be because the clustering method performs better. It's just that it's less likely to find regime shifts in such short time periods. So.
Are there other questions? No? Okay. Thanks again, Anna. Then the next speaker is Tor Johansen.
Good afternoon. First, I would like to acknowledge my co-author, Inger Alina Ononsen. She did a master on some of the data I'm going to present today. First, I'm going to present historical events of abrupt and persistent recruitment collapses in godwit fishes. Then I will also show that there have been shifts in the plankton community concurrent with the recruitment collapses. Then I will also show there's a collapse in foraged fishes for the O group godwits. These data have not been published, the other ones have been published. And then I end up with a summary and a conclusion. First, we have carried out, our lab carried out an annual Bayesian survey since 1919. And what's nice about this time series is that there have been no methodological changes. And so I think it's one of the longest and most consistent time series in the world. And I will show that we can learn probably a lot from a time series like this. Target species have been O-group graduates, but we also counted the number of other species that have appeared. And then we have time series on salinity and salinity temperature, salinity oxygen at 30 fixed stations since 1927. The area we're talking about is south coast of Norway, and we sampled the entire coast up to Oslo and down to the Swedish border. But here I will present some results from a highly industrial area that had a lot of pollution over the years, and the Greenland fjords. And here you can see O-group cod. We started sampling at this place in 53, and you see in the mid-60s there was a drastic reduction in the abundance. This shows O-group pollock, another graduate species. Pollock was never abundant in these fjords, but in the mid-60s, recruitment collapsed. Then we have O-group whiting, and that used to be highly abundant, and we see at the same time, we see this collapse. So we see concurrent collapses in all three species, and there's another remarkable thing. There is no sign of recovery. And this is a recurring event. We looked at possible causes as we measured oxygen, and the oxygen conditions are good. Overfishing is highly unlikely, simply because a species like whiting is a non-commercial species in our waters. And we also looked at contaminants, and it's very unlikely that all species will respond at exactly the same level. And then we looked at habitat changes, in particular bottom vegetation, and we found no concurrent changes. It's a recurring event. It's the same pattern everywhere. It happened in the Greenland fjords in mid-60s, also in Holmestrand fjord in mid-60s, in Oslo fjord already in 1930. This is very interesting because that was before modern contaminants like DDT, but it was occurred during the introduction of water closets. And then we had a recruitment failure generally along the Skagerrak coast in mid-70s, and then a collapse in 2002. Before 2000, gradual increasing neutron loads was considered to be a most likely cause, but it's not, as perhaps you expect, would result in low oxygen, something like that. Actually, what happened is that it affects competition in the fight in the zooplankton community. The event in 2002 is very interesting because this occurred during substantial reduction in nutrients loads, but we had an increase in temperatures. Yes, this is from the time series going back to 1919. This is generally along the two events, and this is the sum of O-group cod, pollock, and whiting. The reason I don't have time to show all the species, and what we see is that in the 20s they were quite abundant. Then there was low abundance in 30s and 40s, and then we had a substantial increase, and then an abrupt decrease in mid-70s. This is where we had regime shift, and then you have another one and also in 2002. And also use stars as a method that probably should not use. And anyway, it's a long time series on the other hand. And you see regime shift occurring. Before I talk too much about this, this is a very important habitat for shallow water fishes, eelgrass beds. And in 1930, a disease wiped out eelgrass all over the North Atlantic. In our waters, it happened in 1933. And because of that, they started to observe or describe bottom vegetation, and we are able to estimate bottom coverage. And as you see, the first regime shift concurred approximately with this eelgrass disease. One eelgrass recovered very quickly in the mid-50s, we had another regime shift, but the two last regime shifts cannot be related to habitat changes. So, as I said, there was not very strong, but a signal of a regime shift in the mid-70s. And this shows bottom water oxygen at the 30 station is in terms of standard deviations, so you can only see the pattern. But that's the important thing here. And then we see when we had this shift in the mid-70s, we saw a substantial increase in sedimentation. Actually, oxygen consumption increased by 50%. But there's no signal before, not after, so it's a sudden shift. And this suggests a shift, something is happening in the plankton community. Then we have this regime shift in 2002, and here you see again oxygen at intermediate depths, and you see a gradual decrease until the lowest level we had in 2002, and then it suddenly jumped up at a much higher level. Again, a signal of, let's see, there it is, and suggests a shift in the plankton community, because there's a balance between autotrophic and heterotrophic processes that determines the oxygen level. This shows, we don't have long time series on zooplankton, but we're going back to 2000, so we should use this time series with caution. But one particular group is Pseudocolons parcolus. They are very important, and they show a substantial decrease. And we've also seen changes in the phytoplankton community. I will not present that. And this here you see the temperature decrease in summer, and the sea surface temperature in summer has increased by about 1.5 degrees. This shows O-group cod, also the same back to 1919. You see a pattern here. And you see the same pattern in older cod. And if you see here, there's been the lowest level ever recorded. And now, look at the older cod. It's been, we hardly catch older cod, even after strong layer classes like in 2011, and we don't catch it. Usually we catch a lot of one group the following year after such an event. So what does cod feed on? They feed mainly on very small organisms, gobies that live for only 1 year. We don't know so much about it because they slip through the meshes of the traditional seine. So, but we carried out studies of these gobies in 1997, before the regime shift and afterwards. And they live for 1 year. This is the parent generation. Then they die, and you have a new generation. As you can see, in 1999, we caught 50,000 of these small organisms per beach hole. That's a huge biomass, buckets of and you see here, 1998 was a cold year, and that will affect summer spawners. These are summer spawners. But now you see, after the regime shift, it's almost totally gone. So the main food for cod during the first winter, autumn or first winter, has just disappeared. So, in conclusion, gradual increase in temperatures, also nutrients, may result in reduced abundance of fish due to abrupt shifts in the plankton community. If you like to read more about this, I've written a book called, from a difficult title, and it's where I propose mechanistic explanation for resilience in the plankton community. And I also propose, which is quite radical and have potentially very significant impact for theories in ecology and evolution. So if you like to read about it, that's the book I would suggest. Thank you very much.
Thank you very much. So are there questions for Thor? Right. Don't be shy. Question? No? Okay, then I have a question. What do you think is the reason that the small gobid disappeared? It's also increasing temperature, or?
It is change in the plankton community because they also feed on. And because of this change in the zooplankton community, this will propagate to higher trophy levels, causing recruitment failure in most species. Because most fish species depend on plankton during early life stages. So it affects the entire fish community. But the interesting thing is, the important thing is that there is no gradual dose-response relationship in the plankton community. And things, for instance, nutrients as such is not a problem for organisms, but it affects competition. And that's why I have this hypothesis about what I call a synergistic relationship in the plankton community that may explain resilience. And mechanistic explanation for resilience is actually what we should search for.
Are there other questions? No? I mean, I think it was nice compared, because finally we see some trying to explanation of mechanism of what is actually occurring in the time series that is a bit difficult to do usually. Okay, so the last presentation is from Maren Kruse, but I think maybe it's online. Oh no, she's here? Ah, sorry. Okay. I read wrong on the website.
So, good afternoon, everyone. Welcome to my talk about possible futures of a fishery system and how we can simulate its fate with a Bayesian network. I think with my talk we move a little bit off topic from ecosystems to fisheries. But many talks already have mentioned today that fisheries are an important part of our society. And at the Thünen Institute, we wanted to simulate if and how fisheries can cope with the increasing pressures in the future. Before I'm going to show you our most interesting findings, let's have a quick look at our study system. The German place-related fisheries is our target system, which operate in the southern North Sea. It's indicated here in yellow. And the target species are place, of course, but they also target the Norwegian lobster and sole. The most increasing pressures we can find here in the system are the increasing installations of offshore wind farms, but also of marine protected areas. So the space where the fishes can go fishing is more and more restricted. We also expect an increase in water temperature, and this can then lead to a redistribution of fish stocks, and of course this has a big impact on fisheries landings and profitability. Because of all these increasing pressures, the place-related fisheries has already shown a decreasing capacity to adapt, and that's why it's an interesting case study for us. So this leads us then to the research questions we had. We wanted to know what are the key factors determining the future of the place-related fisheries. And we specifically focused on the spatial components, so we wanted to identify which areas are the most influential within the system. We also wanted to understand if there are potential benefits of different management strategies to stabilize the system. So to best understand how we approach the analysis of the system and what we mean by SES and adaptive capacity, I will briefly explain this so you can better follow our approach. So a social ecological system, or in short SES, is a concept that captures a system by integrating its ecological components like the target species with its social components like the key actors, in our case the fishes, and its governance structures. And when you analyze fisheries, it's normally recommended, or it's often recommended, to approach them as SES because they are very complex, and normally it's a high interconnection between ecosystems and the society. In this context, the adaptive capacity refers to the ability of the system to adjust to changing conditions. So in our case, how the key actors, which is our fishing fleet, can adjust to changes in fish populations, but also to change in fishing regulations. And now we have defined the two terms, but how do we analyze them? For this, we transferred this abstract SES concept into a Bayesian network. And by this, we make the SES measurable. And this is the process that's also called operationalization. Difficult word to pronounce, by the way. Okay, let's have a quick look at the Bayesian network. We included information from many different sources. So for example, here in yellow, you can see fishing-related data containing information about fish landings and revenues. We have here spatial restrictions related to offshore wind farms and marine protected areas. We also included economic information like fish prices, fuel prices, and also the different costs. And we also considered the socio-cultural information which reflects the fish's behavior here in pink. For the outcome, we looked at two different components here in orange. One is the profitability of the overall system. And as I said, we wanted to know how the adaptive capacity of the system changes with the different pressures. And the adaptive capacity is a system characteristic. It has no spatial dimension. So we created a new matrix we called adaptive capacity potential, or short ACP. And with this metric, this is spatially resolved, and we characterize how much a grid cell would contribute to the adaptive capacity of the system. And its contribution could be high, medium, low, or zero. So some technical details for the network itself. We identified 30 relevant drivers and 34 links or relationships between the variables. We trained the Bayesian network with a high-resolution time series data containing individual fishing trips of 7 years, and they are associated with its revenues and costs. And we averaged these values and sorted them into a grid of roughly 0.05 degrees Celsius. The conditional probabilities, that means the links here between the different drivers, define the strengths of the links of the relationships, and most of them were learned from the data by the software itself. And when we look at the error rate for our target node profitability, for example, the error rate suggests that the Bayesian network correctly predicts 61% roughly of all cases correctly, and for environmental systems and networks, we assume that's fine. So now we had a trained and working BN. We could now start investigate different scenarios to see how the system would develop and its adaptive capacity would change under different pressures. For time reasons, I'm only going to show you a selection of the scenarios we investigated. So, for example, we examined how the system will respond if we close more and more areas to fishing. And we especially looked at what is planned for the year 25, 2030, and 2040. And for the year 2030, we also investigated how the adaptive capacity would change if we look at the worst case, that we reduce fish prices and increase the fuel prices. We simulated climate change by changing the place landings. In this case, it will be reduced most likely. And lastly, it's quite an interesting thing that you can do with a Bayesian network. You can also use it as a diagnostic tool to simulate different management strategies. In this case, we looked at medium profitability, so we wanted to simulate a system that has an average level of profitability, and for this we set the node to a specific state. And then we look at the rest of the system, how we would have to manage the other drivers so that we can achieve this. So this was roughly our approach, and I will show you now some of the findings. As a result, our BN creates spatially explicit maps indicating where the place fishery operates. And in the maps you can see here, we indicated the likelihood that a specific grid cell will have a high adaptive capacity potential. On the left here, the baseline scenario depicts the system based on our data in 2020. And then these maps show the increasing spatial closures from 2025 to 2040. And the maps are color-coded that you see in lighter colors or yellow. A low likelihood that a cell has a high adaptive capacity, and the darker the area, the more important the cells might be for stabilizing the system. Yeah, when you look at the details, you can see by the increasing proportion of the lighter areas that these increasing closures lead to a drastic decline in the probability that areas have a high adaptive capacity, and this is especially true if we look at what is planned for 2040. You can also see that the southern part of the North Sea seems to be quite relevant, as the darker spots kind of concentrate here. As I said before, we focused our analysis specifically on the year 2030 and simulated further scenarios for this year. And here on the left, you see again the map you've seen just before, the spatial settings we assume for 2030. And then on top of that, we modeled the economic price changes, the changes in place landings, and here what happens to the system if we simulate a medium profitability. The map is color-coded as before, and if you look at these two, it looks like that economic fluctuations doesn't have a big impact on the adaptive capacity, but if we then look at the place landings and the climate change effects, you can see that the likelihood that a grid cell has a high adaptive capacity is drastically reduced. And here, the map indicating a management strategy, it looks like if I aim for a medium level of profitability, the adaptive capacity potential of the system would be enhanced throughout the system. So overall, we found that spatial closures and climate change have a significant effect on the adaptive capacity of the system, outweighing economic fluctuations. So if we now go back to our research questions, we found that the loss of space due to spatial restrictions to fishing grounds and the climate change effects on fishing landings can significantly impact the adaptive capacity of the system. The southern part of the study area seems to be particularly relevant in managing the system, and if we aim for a medium level of profitability, the adaptive capacity may be enhanced throughout the system. With our study, we can also see that a Bayesian network can help to analyze complex social ecological systems. And with this, we can see and identify future trends. And also a great advantage is that we can produce highly resolved spatial maps, and they are quite easy to understand. So this allows us to maybe prioritize areas for management, and based on that, we can then also develop more localized management strategies like co-location or multi-use MPAs. Thank you very much.
Thank you, Maren. Are there questions?
Thank you for the nice presentation. I'm getting involved in building Bayesian belief networks,
Yes.
and I'm struggling with the issue, so I have some questions on the building of your model. First, I didn't see the fish in the model. Maybe I missed it, but...
No, the fish is represented by the landings, more or less, so it's not that we actually model the fish stocks itself. It's represented by the landings, so the amount of fish we take out of the system.
Yeah, but so as I read it, it looks like the more you fish, the more landings, or the more capacity, the more landings. But the fish is not involved in the process. I couldn't see it in the model. But what I was wondering is if you had tried different model configurations, and if that would lead to different results.
Well, it most probably will lead to different results, but we had quite a different, several workshops on it, because the conceptual model, of course, is the key to the whole Bayesian network, and you should be sure in how you link the different drivers. So also, this is not a whole representation of the whole system, but more of the causal relationships we identify for the fisheries. So I think that the Bayesian approach is not that I model the whole system, but if I want to represent the causal relationships of the fisheries, I might reduce the number of drivers I consider relevant. And then, of course, you need to know which ones you want to link. It's not that there's the best BN. I think it's more, you should be sure if there's a linkage or not.
Yeah. But so this model is a compromise after discussions with...
Yes. We discussed with many people quite many times. I think I don't know if you were involved actually. Yeah, so, and then also, of course, the aim is to have as few drivers as possible or linkages, because then, of course, the BN performs better.
Okay, and one last question on the same line, if I can.
Yeah, sure.
In my experience, one thing that these models struggle to describe is feedback loops.
They cannot.
Which are quite critical in representation and thinking about the system. For example, I mean, fishing more leads to less fish, which leads to less fishing and so on, or vice versa. So have you thought, has this been a part of the debate or when you have built the model? And have you thought of ways to circumvent that limitation of the model?
So I think, of course, this is something, if you decide you do Bayesian networks, you cannot implement feedback loops. This is a limitation you have to be aware of when discussing the results. And to me, or I think also that's what we discussed in our group, is it can be one tool you can use to get an idea, but it's only one way of analyzing the system. It's not that it gives you the answer. It only gives you a good answer if you ask the right questions. You cannot expect it to show you these feedbacks. Then you have to use a different approach. So yeah.
Thank you.
You're welcome.
I hope we can discuss after.
Yes, of course. Yeah. I'm happy to.
Are there other questions? Maybe I have one.
Yes, sure.
Yeah, I was thinking, because from what you show, I would expect that if the fuel price increase and the fish price go down, I would expect the maybe fishers will not go out, or it will be not convenient for fishers to fish. So I would expect a much higher impact of this economic part on the adaptive capacity. Why is not? Why do you think is not that important?
Yeah, there's an unfortunate reason for this, and I didn't mention it for time reasons, but the BN can only work within the frame you set it for training. And we had a data set that lasts until 2019, and the fluctuations weren't that big. So all the big impacts like Brexit, the fuel crisis, is not included yet. So once we have new data, we can train the BN, and then the range of the node states will be different. So now I can only predict within the range I have from the past. So once we have the complete data set and you have a bigger fluctuations, you probably most likely will see impact. So it's because of that.
Okay. Thank you very much.
You're welcome.
So I think we arrive at the end of this second part of the session. I think we learn a lot, like that we have to be very cautious of the method we use, and also about the funding feedbacks that can explain tipping points. So please come back for the next part of the session that will be equally exciting. Thank you very much.
Hello. Hi. This is, can you come in or take your seat? We are about to start with the last session of today. And before we go on, if you plan to attend the reception tonight on the tall ship, please don't forget your name tag. This will be your entry ticket. Otherwise, you will not be able to get on board. That is Jerry Tiputra from North Climate, actually here in Bergen. And we are moving a bit to changes in driving mechanisms and their potential impacts on ecosystems.
Right. Thank you very much. My name is Jerry Tiputra, as Bergen mentions. I'm a researcher at Bergen Center for Climate Research here in Bergen. And I'll speak about the detection timescales of environmental drivers in the interior oceans. I'd like to thank the conveners, as well as the co-authors, Gradual and R. Olsons. So quick introductions, why we care about detecting anthropogenic climate change signal robustly in the interior is because it helps us to improve our understanding of the Earth system response to external forcings, such as the CO2 emissions that we put now. Also, it helps us reduce uncertainty in the future climate projections. We can create a better model, improve the predictions of the models. With that, we also feedback the observing community in terms of where we need to put the monitoring network to detect these changes. And in the end, the goal is to develop a future efficient mitigations and adaptations plans. So in this exercise, we have looked into projections of 4 key stressors. That's the temperature, salinity, oxygens, and acidifications, pH. And we apply a suite of 17 IPCC class Earth system model. So this is all the highly complicated models that are used in the assessment report of the IPCC. And then finally, we also assess the impact of mitigations. If we do climate mitigations by reducing the CO2 emissions versus business as usual, whether we can see any of these changes in the interior oceans. So in the past studies, many of the studies have mostly looked into changes at the surface, especially in the oceans, right? So like this, for example, a study by Lester Kwiatkowski shows the changes in the temperature, surface pH, upper oceans oxygens, and surface nitrate. So all of these signals are quite pronounced, and we understand that there's these changes, and they are quite vary from scenarios to the other. And Stephanie Hansen's and colleague done this emergent constraints, time of emergence. That is the time when the anthropogenic signal emerged from the natural background. So this also has been done for the surface parameters, the temperature, pH, the surface primary productions, and oxygens. And you see that the pattern is not uniform. The emergence of the stressors are very different depending on the variables and also depending on the locations. What I like to emphasize here is that the IPCC report, the last one, states that we're probably overlooking the vulnerability of ecosystems in the oceans because the lack of understanding of climate change in the interior. Because most of the study, again, has been looking at the upper ocean and surface, but not so much on the interior. So this is, prior to this, we have done a very quick study where we do Earth system model simulations, where we do this very rapid CO2 emissions to the atmosphere up to 4 times CO2, and then bring it down again to the pre-industrial level after 140 years. And we want to see whether we can actually see these signals at the surface, and how is that difference in the interior oceans. So in the middle here, in the middle panel here, showing the overturning circulations. Red is the circulations at the surface, and then blue is the interior oceans. You are mostly familiar with this. And on the left panel, then you see this, the North Atlantic projections of the dissolving organic carbon, and then on the bottom here is the pH. And what you will see is that the signal is quite reversible at the surface or the upper oceans for the dissolving organic carbon as well as the pH. But as you go to the deep oceans, then you see this is somewhat smoothed out, the signal. You still see the signal, it's smoothed out, and it lasts a bit longer compared to the surface oceans. So The signal is reaching to the surface, but it's delayed somehow. And if you look at the different regions, slightly a bit further, older water mass in the Indian Oceans, you see a very similar pattern at the surface, but in the interior it's very different. You see this a very delayed changes and lasts very long. So depending on your definitions of tipping point, this could be one of them, where the system actually changed and lasts for quite a long period of time. And could be vulnerable, could have a significant impact on the marine ecosystem below the surface. So this is what we are looking at now, but we're looking into real scenarios from the IPCC. That is the two SSPs, one with business as usual, and the other one is with medium mitigations, reductions of CO2 emissions. And we look at all 17 Earth system models that we have all of these variables. And the concept that we've used is called the time of departure, and you can illustrate it by here. We have this natural envelope of variability. This is from the model simulations under the pre-industrial period. For every grid point, we have this window of natural variability. And every grid point, every depth level has a different window of natural variability. And then the green line here is the projections for that specific grid point. For example, here for the temperature. And then the time of departure is the time when it's just exit this natural range and stay there for at least 10 years in the model. Yeah? We do this for every grid point, for every models, we average them, and we get these maps. Okay? So for every column, it's different stressors. The first one is temperature. Second column, salinity, oxygens, and the rightmost is pH. And from the first row towards the end is we're going from the surface to the deep oceans. So a lot of information. When we see this stippling, that's when the model is less in agreement. When you see a clear without any dots here, that means the model is quite in convergence in terms of the time when we see this signal emerging. So red color is indicating an early detections, an early departure, and then the bluish and purple is a bit pushed towards the end of the century. So what we'll see here, I'll just mention some of the key feature here, is that for every variables, you see that the pattern is not similar when you go from surface to the deep, especially in homogeneous. As you go for the different variables, you also see, again, different pattern, except for the surface for the temperature and oxygens. Here, the oxygens is mostly constrained by the temperature and salinity for the surface. Everywhere else is quite different. pH here, mostly red. That means that the acidification signal, as we know, emerging quite fast and quite pronounced relative to the background because of the chemistry of the seawater. And you see that as we go to the deep, the signal that will emerge early is the Atlantic and the Southern Oceans. And this is related to the ventilation regions. You actually see the signature here of the intermediate water mass that's going from the Southern Oceans into the deep oceans. And also the ventilation region in the North Atlantic will emerge earlier. So I'll briefly mention what drives this spatial pattern, why they are so different, right, between different variables. So here, for example, I'm showing the time of departure for temperature at surface and a bit much deeper here at 2,000 meter depth. And you see the pattern are significantly different from one another. And in the middle column here is the change in the temperature. That is the simulated temperature change. And then the right here is the standard deviations or the natural envelope, envelope of variability of the interior oceans. So what you see here is at the surface, the pattern where we see this reddish color is very much following these regions where there is this low envelope. Yeah? Regions like the equatorial Pacific, where there is the El Nino ENSO variability, then you see this much delay time of departure. The same thing happens in the interior oceans, where we see this reddish color. They are regions that represent very stable and mostly vulnerable regions that is sensitive to changes in the future. So I like to highlight the tropical Atlantic here as especially important because we get this early emergence in many of the variables actually, temperature and salinity as well. And this is because the regions are very stable, but most of these Earth system model project big change in the tropical Atlantic. And here is the oxygens. You don't have to go far for oxygens. So here on the surface, and this is 100 meters, and you immediately see very different the time of departures. And the reason is because at the surface, the oxygen is mostly driven by temperature and salinity, but as you go to the bit deeper here at 100 meters, the export productions, the biology, play a bigger role in controlling the natural envelope, because they provide these organic matters that eventually consume the oxygen. And this slide here shows that the first row is the depth of earliest time of emergence under business as usual, where we can see the earliest departure of anthropogenic climate change. And then at the bottom row is the earliest time of emergence. So first, if you look at the bottom, it's mostly in the first half of the color. That means that if we measure all of the 4 stressors here throughout the water column, we will see the change, the model, we'll see the change already before the mid of the century. And on the top panel, you see that except for the pH, you see, most of the change that we will see detect the first time will be below the surface. So the interior oceans will likely have detectable changes prior to the surface, according to the model. And this I just wanted to highlight that for the salinity, which is a good indicator for circulation changes, there's an early detection here along the Gulf Stream. And this is closely related to these reductions in the overturning circulations in the Atlantic. So if you see all of this model similar to reductions in the overturning, we'll have this salinity anomaly, that is less salinity is being transported northward. And this is, our study shows that it's strongly correlated to the AMOC, and that if we want to detect the circulation changes, especially this overturning, is actually that the time of departure for salinity here is actually, you get a detectable signal about 10 years earlier than by observing the overturning circulations. And lastly here, I'd like to show what is the impact if we go into business as usual versus the mitigations. This is a relatively strong mitigations. As you see, the CO2 concentrations are quite different between the two scenarios. At surface, as you may have already guessed, the color will be slightly towards bluish color. This is a surface for all the 4 stressors, and you see this from reddish color becoming slightly bluer color, except for the pH, because pH already emerged quite early. But now if you go to the interior, I'm showing here 2,000 meter depth, you're probably not going to be able to tell the difference. Yeah? It's very similar in terms of the time of changes in anthropogenic signal. And this is just to highlight the departure of multiple drivers. So by 2030, most of the signal that we will see are associated to pH changes here in the upper oceans, and this is in the lower oceans. But by the end of the century, then, many of the world oceans will have all of these 4 stressors emerge outside of the natural background. And it's 80% in the interior, where it's only about 50% at the surface. So to summarize, the majority of anthropogenic climate change signal, especially warming, salinity change, and deoxygenations, we show from the models is most likely will be detectable in the interior first, than at the surface. And this is because the low background natural variability of the interior oceans make it more vulnerable to future changes. Acidifications is the first one to emerge, followed by the warming and oxygen changes. We show that temperature and salinity are actually good indicators to tell about circulation changes, especially the overturning circulations in the Atlantic. We show that whether we do mitigations or not, the interior is not going to make a big difference, suggesting that if we stop emissions today, all of the warming, all of the oxygenation signal, acidification signal, all of these are already in the oceans, and they are actually propagating already as we speak right now. So it will emerge eventually. And some of the key regions to monitor is the tropical Atlantic, North Atlantic, and the Southern Oceans. With that, I thank you very much for your attention.
Thank you so much. Do we have questions in the audience? If not, I was wondering if you have if you look at time of emergence, then this is very much dependent in the surface ocean also on the ensemble size. So if you have an ensemble, you would have a more robust detection. I guess that is not so much of an issue in the interior ocean where the variability is not as large. Do you have an idea whether or not you would have a more robust detection timescale if you were to look into a larger ensemble?
I have the same feeling with you. I think in the interior, the signal propagates much slower and less dependent on the natural variability. That the uncertainty is mostly intermodal uncertainty rather than specific model uncertainty. And that's why we choose 17 models. And we have actually a matrix to say how uncertain this is. If there's a big spread among the models, that means that the time of detections is uncertain. Yeah, and so I think it's the intermodal difference that is more important for the interior.
So having a larger ensemble would not resolve our oxygen robustness in terms of the signal there?
I don't think so. Yeah, I think it's more dependent on the scenarios and also in the different models.
Thank you so much. Then we will move on to our next speaker. We have Jiaying Chen here, and we are hearing about detecting and forecasting nonlinear dynamics for copepods.
Thank you so much. And hello, everyone. I'm Jiaying Chen. I'm a PhD student from Memorial University and Canada, and under the supervision of the Dr. Jing Gao and Dr. Tyler Eddy. Today, I'm glad to present my research applying empirical dynamic modeling EDM to copod on the Grand Banks. Here's my outline. First, I will introduce what is empirical dynamic modeling, EDM, and then show the results of the EDM application in copod population dynamics. Question, what is empirical dynamic modeling and why we use that? The word empirical is referring that we are going to do these things based on the data, and the word dynamic refers to the fact that we don't need to make assumptions about the relationship between variables, and the relationship of the variables don't have to be linear, and they can change over time. We use the EDM to forecast the species population dynamic in the ecosystem. So how the EDM works, the ecosystem is a high-dimensional system. For the better display, we just assume the ecosystem, the manifold M is a three-dimensional system with the dimensions X, Y, and Z. As you can see, this system is not a linear system, and the relationship between the variables are very complex. And the motion of the manifold can be projected onto a coordinate, forming a coordinate axis, forming a time series data. So, for example, X is zooplankton data, and Y is phytoplankton data, and Z is fish data. The dynamic of the zooplankton can be affected by the phytoplankton data and the fish data. So each time series in X, Y, and Z is a projection of the original system manifold on this figure. So if we have the phytoplankton, zooplankton, and fish data, we can project them back to reconstruct the original system like the M. But in reality, sometimes we don't have the phytoplankton data and the fish data. We only have the zooplankton data. So in this situation, how can we reconstruct the ecosystem? Sorry, it's a mistake. Taken theorem is crucial for the EDM that allow us to recreate a shadow version of the original manifold simply from the single variable time series data. So here is the example. We just use the time series of the zooplankton X and a dimension of the X with the leg of tau and another dimension of legs with the legs of 2 tau. And as in this figure, the top one is unlagged, the second one is lagged by tau, and the third one is lagged by 2 tau. We use these 3 time series to reconstruct the shadow version of the original system MX. The MX preserved essential mathematical properties of the original system M, and the shadow version MX will map 1-to-1 to the original M. So in our example, in EDM, it is possible to use historical data only from the zooplankton abundance to forecast the zooplankton abundance in the ecosystem. And the EDM is increasingly used in ecological to to forecast the population size in the ecosystem. Here are the 2 publications. The first one uses the spawning stock and the environmental variable in EDM to forecast the recruitment of the salmon, and the second one uses the EDM to forecast the population changes the population changes of the Pacific siding tied to the climate change. Also, the EDM can capture the complex and the nonlinear relationship between the variables, but it also has some limitations. The first one is EDM does not estimate uncertainty in predictions. To overcome this problem, we implement EDM via Gaussian process JP regression, because the JP regression can handle the uncertainty in predictions. And the second one is EDM requires a long time series, but in reality, our time series may be very short. So there are 2 common methods to use to address this problem. The first one is the spatial method, and the second one is the concatenate method. In real-world application, our time series data may collect by multiple stations, and we use this time series data in spatial replicate in EDM to increase our data volume. So for the spatial extension of EDM shown in figure A, we construct the embedding vector for each location, and the embedding vector is the same thing as what I talked before in showing in this figure. So this method only uses the lag of time series to reconstruct the system. It doesn't to account for the population dynamic, as the focal station may depend on the states of its neighbors. The lags from the spatial, the neighboring station may provide additional information about for the forecast. And the figure B and C shows the true spatial EDM. The red box shows the S EDM that include both the lags of spatial neighbors and the lags of the focal station. So this method not just increase our data volume, and it's still to make our data contain more information. So the difference between the naive SEDM and the informed EDM is that in the informed EDM, the coupling scale is decay with the distance. And this figure shows the local method and the concatenate method. In the local method, we just use the time series at the location n to make the prediction at the location n. But in the concatenate method, we use the time series data at the multiple stations pulled together to make the prediction in each single location. And this is our case study. Copod is the most abundant zooplankton on Earth and one of the most abundant species in the Northeast Canada Ocean is the Calanus marcus. It is a rest-sized crustacean and most distributed in the North Atlantic, and it is a short-lived species and quick dynamic. The temperature of this species range from the -2 to 22 degrees, and the copod plays a critical role in marine ecosystem because it is a key food source of many fish species such as cod, herring, and mackerel. So understanding about the population dynamics of the copod is essential for the management and the conservation of the marine resources. So we focus on the copod population on the Grand Bank. These two maps shows where is Newfoundland is in Canada and where is the Grand Bank. And we use the copod for survey data collected by Fisheries and Ocean Canada Atlantic Zoo Monitoring Program, AZMP. So this figure shows all the AZMP oceanographic stations. Since some survey stations discontinues between years, so we just select 11 stations, the 7 stations on the southeast Grand Bank and the 4 station in the Flemish Cap. And we set the 2001 to 2012 copod for survey data as the training data, and we set the 2013 to 2015 copod for survey data as the testing data, and we applied a 6 method showing here to forecast the copod abundance on the Grand Banks. And we implement EDM and SEDM via Gaussian process JP regression. And we use the training data to train the model first, and I use the testing data to check the forecast accuracy. And we measure the forecast accuracy with the root mean squared error and also with the R squared. R squared is the percent of variance explained by the model. So here's my results. In this table, we found that the naive GPS EDM local method has a best forecast accuracy, forecast performance, because it has the lowest RMSE value and the highest R squared value. And in this figure, the blue points are the observation value in combined 11 stations, and the solid line is the prediction in the combined 11 stations using the naive GPS EDM local method. And the second figure is the correlation between the between the observation value and our predictions. So here's my conclusion. Leveraging spatial information in EDM may generally improve accuracy of prediction. And we all know the copod species may be affected by temperature, and the EDM can detect the relationship between the environmental drivers and the population dynamic of species. So how can we use EDM to answer the climate change questions? We are going to predict the Grand Bank copod population with climate covariant as additional dimension, such as we include the temperature as a predictor in our delay coordinate system. And we need to make the multivariate embedding vectors that is different from the univariate embedding vector that we used in our current EDM. And the prediction of the copod population, it depends not just on the lags of copod time series data, but also on the lags of temperature time series data. Thank you.
Thank you so much for this very interesting talk. We have a question.
First of all, thank you. That talk was delivered so clearly. Thank you. One question I had for you. The EDM that you built is based on these lag in the state variables to sort of reconstruct the underlying attractor.
Yeah.
But in Taken's theorem, it also says that the attractor needs to be an attractor, first of all. It needs to be smooth, too. Now, when you're dealing with these fishery data and in the ecosystem, there's so many variables, so many nonlinearity. Is that assumption violated, or maybe there's something more that you have uncovered in using this approach, despite the fact that you don't have a smooth attractor, perhaps?
Okay, I think the EDM method is kind of like the machine learning. We just input the past data to train the model, and they can give the forecast of the 1 year forecast of this species. So I think in the taken theorem, we just need to fit the function f in that to get our predictions.
Yeah, thank you for the presentation. I have a question regarding the forecasting skills of the model.
Yep.
My experience is that usually when we want to evaluate a forecast, and that's what's been done in weather forecast in earlier times, you compare with the easiest model that you can build, and it is tomorrow is going to be like today. So that's a super simple model. So let's say, for example, my forecast for tomorrow's weather in Bergen is sunny, because today is sunny.
Okay.
So I was wondering if you've tried to evaluate how much your model beats this simple projection that next year is going to be like this year.
That's a really good question. So I also think it's hard to forecast the next year based on this year, but it's not just on the base year, it's based on the previous lots of year to make this forecast. So I think the answer is actually, I really don't know the relationship between the variables, but in this EDM, we don't assume the relationship between variables, so just based on the data. So if your data is sunny, so the next year the data also is sunny. Is that answer your question?
No, not really, but we can talk
I think we have to move on. Thank you so much. There's another question. You can maybe take it afterwards. Thank you again.
Thank you.
Thank you so much. And we have now Sandra Emry coming and talking about thermal performance curves under multiple drivers.
Okay, thanks everyone for coming. Just as a quick preamble, I'm Sandra, I'm doing my PhD in the University of British Columbia. I totally forgot to add my collaborator, who's my supervisor, sorry, to Chris. If he watches this, he'll definitely be on the paper. So Dr. Chris Harley should be up there. You'll also notice that well, maybe you haven't, but I changed the name of my talk from what is in the abstract, and that was because I just submitted this chapter to my PhD committee, and there was some adaptation critics on my committee that didn't love that I had local adaptation in the title and thought that that was a bit bold of me to put that right in the title there, given the data. So I would be happy to speak to other people about if you think deeply about adaptation. And then lastly, before I launch into it, as a settler to Canada, I think it's my responsibility to do what I can to advance Indigenous reconciliation. So I like to start out my talk just letting people know that I feel very grateful to have conducted this research on the traditional, ancestral, and unceded territories of the Musqueam, Coast Salish, Tsleil-Waututh, and Squamish nations. Okay, so it's no surprise to everybody in this room that climate change is happening across the globe, and we've been studying the response of individuals and populations to warming for decades now. And it will also be no surprise to everybody here that warming is not the only thing that's changing across the globe. We have other anthropogenic stressors that are happening both locally and then globally as well, and lots of different talks here this week on some of these, hypoxia, ocean acidification, noise pollution, et cetera. But much of the empirical work on multiple stressors to date have been done with ANOVA type experiments where we manipulate maybe a couple different levels of 2 or 3 different stressors. And while those approaches are definitely valid, we know that response to these stressors in general is nonlinear. And so by doing these 2x2 factorial manipulations, we can miss really important tipping points or thresholds. So one other approach to doing work on multiple stressors is to build reaction norms. Here I'm showing a thermal performance curve. So we've got temperature on the x-axis here, and then some sort of proxy for fitness on the y-axis. And we typically see this like exponential rise in temperature up to some optimum, and then a sharp decline in performance at higher temperatures. But we don't really have a great understanding, so we can also use these curves then to estimate what I call thermal traits, one of those being what I call P max, which is just the maximum performance that we see at the thermal optimum, which is the second thermal trait, and then CT max, which is the critical thermal maximum, or where fitness or performance goes to 0. But we don't yet have a great understanding of how this thermal performance curve will change with additional stressors or with interspecific variation in populations, which I'll get into. So one estimate could be, or one scenario could be, that we would see a decline in that P max, but maybe T opt and CT max, or the variables on the x-axis, those stay the same. Another option would be that we would see like a contraction of the entire curve, where we see shifts at the upper lethal limits or in CT max. Or subsequently, we could see a kind of like a leftward shift in the whole curve, where we see even impacts at T opt as well. We see that thermal optimum shifting to the left. So the questions for my research project are quite different than what you've seen in this session so far. I'm going to kind of zoom in on a specific species and a specific system. And I asked, how does a second environmental driver alter that species' thermal performance curve? Does source population mediate those shifts in the curve or in the thermal traits that we estimate? And then lastly, how do shifts in thermal traits vary across levels of biological organization? The system that I work in is in the Salish Sea, which is kind of this whole area here. This is called the Juan de Fuca Strait, and then the Strait of Georgia here. And then I work in the intertidal zone of the Northeast Pacific. And so this is an estuarine system. As you can see, this light green whitish water here is freshwater plume from a major river source in the area. And it has really high outflow in the spring, particularly, that impacts circulation really in this entire system. But we see this seasonal decrease in salinity, sea surface salinity, on this side of Vancouver Island, which is this big island here, that we don't see on the west coast of the island. It stays with high salinity year-round. We also have a dichotomy in the air temperature here. So the Strait of Georgia experiences warmer air temperatures that impacts the intertidal zone, whereas we have the colder maritime water on the west coast. My species that I'm going to talk about today is Fucus distichus, which is a really common species of brown algae. It's incredibly ecologically important as a foundation species for the intertidal zone. It provides thermal refugia for lots of different algae and invertebrate species. And different species of Fucus can be found almost globally. It's a very plastic species, so it has the ability to create different phenotypes with a single genotype, and it also has really limited dispersal. So typically the gametes disperse about 1 to 2 meters away from their parent thalli. And so because of that, we often detect local adaptation in this species. My sites are indicated here with the orange triangle here. I'm going to call that Nanaimo, because that's what it's called, but if you're just trying to remember that. And this is the warm, fresher site, and then the blue star is Shirley, and that is the cold, salty site. And you don't have to take my word for it. So this is mean daily salinity from a decade, so 2009 to 2018, and this is mean salinity across each day in late spring to summer. So you can see that Shirley remains consistently high, whereas we see this dip late spring, early summer in Nanaimo, and it gets down to almost 15 PSU there. So what we did is we went out and collected reproductive individuals from the field, brought them back into the lab, and germinated them across 7 different temperatures, so from 2 to 28 degrees, and at 3 different salinity levels, 5, 15, or 30. I measured % germination in each replicate, and then of the alive individuals, I measured growth. I'm not really going to talk very much about it, but you can fit lots of different types of models to thermal performance curves, and I fit the Sharp Schoolfield model, which I'm happy to talk more about if you have questions about it. Okay, so I'm going to show a series of different thermal performance curves now, starting with the Shirley population, which is the cold, salty population. So again, that's temperature on the x-axis, and this is now % germination on the y-axis. So when we measure them at 30 PSU, we see this kind of typical shape for a TPC or thermal performance curve that we would expect. Now when we measure them at 15, we see a bit of a contraction, a decline in the height of that curve. And then when we measure it at 5 PSU, we really see that thermal performance curve dropping off across all temperatures. Now, when we compare that now and take source population into consideration and look at the Nanaimo population that does experience seasonally fresh waters, at 15 PSU, we see it's fairly similar to the 30 PSU and maybe a kind of a similar decline, although slightly less so than the Shirley population. And at 5 PSU, so this population doesn't experience salinity this low at 5 PSU, but we definitely see a huge difference in their thermal performance curves across populations. And so just to look at that a different way, we can then extract the thermal traits from those estimates. So these are the estimates extracted from the model fits with bootstrapped confidence intervals around. And so this is maximum germination, so the height of the y-axis at the thermal optimum, and we see that large difference between 5 and 15 PSU for Shirley. And we don't see as much of a decline in the Nanaimo population. Similar for the thermal optimum, we see a big difference in that thermal optimum for Shirley that we don't see in Nanaimo. The results are a little bit messier for CT max, and that's to do with the model that I'm fitting, but still we see that kind of that same general trend where we see changes in the Shirley population, even from 30 to 15, that we don't see at all at Nanaimo. Okay, and then very quickly for the last one, so how do shifts in thermal traits vary across levels of biological organization? I've only shown you germination results so far, and I also measured growth. So these are just those 6 curves that you've already seen, just all in one. And when we compare that to growth, we see a fairly different story where we see really no change even in the Shirley population. So that's the cold, salty population, and they typically grow quite well across all levels of salinity. And in Nanaimo, we see at 5 PSU, we've seen a large shift to the left or to cooler temperatures in the T-opt and CT max. And just for this sake of brevity, I'm just going to show you one of the thermal traits that we estimated from those curves, which is the maximum growth or rhizoid length. And so I'm just comparing that again to something that I've shown you here already. We see that big sensitivity in Shirley's P-max and even in Nanaimo's, where we don't see that at all, interestingly, for the Shirley population. And then we do see a small decline in Nanaimo. So it's pretty tricky to summarize each of these 3 questions independently because they are kind of all interwoven. It's really not possible to answer them independently, but so we did see, just with that Shirley population, we saw that P-max and T-opt declined quite a bit with a smaller decline in CT max, but that was definitely mediated by the source population, which is likely local adaptation. And then we saw different sensitivity in the levels of biological organization that we looked at, with germination being much more sensitive than growth. And so thank you to my supervisor and to my lab members, especially 3 who helped out in the field a bunch, and to DFO, which was one of my funding sources.
Thank you so much for this presentation. Do we have questions in the room? Yes.
So I'm trying to figure out how to word this question, but I've been going back and forth between this session and the one on kind of species on the move. Okay. And one of the things that's kind of come up a couple times in the other session is that oftentimes if you look at larger and larger spatial scales, you're getting closer to the fundamental niche of a species rather than the realized niche, and sometimes that can help with making climate change projections, but by looking at those larger scales, you're ignoring local adaptation. Mm-hmm. So I guess maybe this is more of a comment that you can kind of talk to, but it seems like that, you know, I think that some of the people who are moving towards larger and larger scales aren't thinking about like maybe like rather than getting at realized niches, you're getting at local populations that might be genetically adapted, which is what you seem to be like seeing in your study.
Yeah. I feel like maybe that was did you ask a specific question or are you just commenting? I just want to make sure I didn't miss it. Yeah, no, I agree. I think there are like species distribution modeling that do take into account like latitudinal gradients in responses, but there are lots also that don't. And I think we do know enough about life history traits of lots of species to know that we could expect certain species to be locally adapted and therefore have very different responses, or ones that exhibit a lot of phenotypic plasticity. So I think it's this trade-off of wanting to do more of like a macro ecological approach and getting like the broad scale, broad brush patterns, but then maybe missing some of that fine-tuned information. So I think it likely just depends on your question, like for management purposes, for like place-based science, and I think you definitely want to take things like this into consideration. Yeah, thanks.
We have time for one more quick question.
I was just thinking about how much you know about either the physiological mechanisms in response, like it's not just any other stress. You know, you picked a particular kind of stress, so there's, you know, whether it's similar physiological mechanism, whether there's genetic upregulation that's, you know, connected between these things, or just how much is known about that?
About
those
why we see
the two stressors that you, and you might have.
Yes. So, I mean, I didn't measure mechanism, so I can speculate, which I love to do. And so I think it could be a few different things. It could be like an energetic deficiency. You're dealing with one stressor, and especially if you're not locally adapted to dealing with that stressor, it probably is very taxing on the organisms to mount a stress response. And then if you are then dealing with a second stressor, you just don't have the energy reserves to be able to upregulate heat shock proteins, which are incredibly energetically costly. So I think that could be one. And then a second kind of like grouping of mechanism could just be like physical damage. So like hyposalinity causes an influx in reactive oxygen species, and that also is energetically costly to upregulate chaperone proteins that can then scavenge those. And if you're not able to do that, then that's going to cause damage to the photosystems that allow you to photosynthesize and then create more energy to deal with that stress. So I think it's a really interesting area, the mechanism, and I wish I had more capacity to deal with that. I delve into it a little bit in a different chapters, so yeah, good question, thank you.
Thank you again. I think with that we will close this session, and all the speakers I think will be happy if you have questions throughout the week, so just approach them and have discussions also tomorrow during the poster session. And again, thank you to all the speakers for today. I learned a lot. I hope you did too. So we were very excited to have that many people in the room, and also people following online. And yeah, enjoy sunny Bergen. It is always like that.